It is not allowed Google Meet.
Yeah,
you have to
actually,
go for a alternate. No.
yeah,
But where are the others?
I don't know why aren't they joining.
Okay. So, okay, I will call Madhu.
Yeah, Madhu sir
Yeah,
is here.
sir?
Sir is
I
here.
got it. I got it. I came online.
Okay, okay, good.
I'm just want to share this one to Minu. Hello? Just a
Sir.
moment.
Yeah, yeah.
Just a moment. I'm sending this link to Minu.
Oh, okay.
You guys already sent. Hello?
Yes, sir.
Is it good? Audible?
I'll just call her so that yes. For me, I am fine. What about you all guys?
Yeah, I think it is good.
Am I audible to all of you?
Yes, yes.
Yeah, sir,
Yeah,
audible.
excellent. So, excellent. I just want to call my student. So just give me a 1 moment. Okay, meanwhile, I can share my screen. Hello, Minu. I sent a link. Just see that one. Yeah, thank you. Enjoy. It's a Google Meet. Yeah, thank you. Have a nice day. Okay, now we'll come to the PowerPoint. Almost. Am I audible to you?
Yes, sir.
Yes, you are
Yes,
audible.
sir.
Yes. So I have to add a presentation, right?
Right, sir.
Yeah, please share this.
Okay, you enter your screen. Are you getting the screen?
No, not right now.
Could you see my presentation?
No, sir.
Okay, now just a minute.
Share screen
So
option.
Present now. Option is there.
Yes, please. Is it right? Could you see this?
No, no. Yeah, something
Yes,
is coming.
Yes, sir.
Yes, yes.
Okay. Okay, fine. Thank you. Yeah, this presentation you have seen yesterday. So we are seeing we learned about the radar and meteorology. So and the atmospheric targets, right? And sizes of the things, which is very important, is the aerosol for the lidars, cloud droplet for the cloud radars, and rain droplets for the precipitation radars. So these are the examples of the weather radars. So they works with the distributed targets, not the point targets or the hard targets. These are the soft targets or the distributed targets. And one more is their refractive index gradient. They will be used for the wind profilers. We will learn that one in the later stage. But this is also a part of weather radar, right? And we have seen the various application of the weather radars, and there the radar is an electromagnetic system. So we are going to say now the electromagnetic spectra. So because now I want to show how the radar is working. For that, what is electromagnetic spectra and which wavelength I am going to use. It's a down one is the wavelength, whereas the top one is the frequency. They are connected. You already know the equation. V is equal to nu is equal to n lambda. The frequency n is equal to c lambda. C is the velocity of the light. So that way you'll get, and we usually see only the Vibgyor color, that is 400 angstroms to 4000 angstroms to 7000 angstroms, or the maybe in a nanometers 400 to 700. So green light is most dominant for our visual eye. So and after the red is called the infrared, so which is having in terahertz frequency. Whereas if you go into the ultraviolet, so they are under 10 to the power of 6, or the wavelength is 10 to the power of minus 8 meters. So, but we usually speaks for the radar purpose. This is the region, microwave region. This is the region where we think. So, like a if it is a 10 to the power of 0, that is 1 meter, and 10 to the power of minus 3, so it's a like a millimeter. So this is what used for the cloud radar, 8 mm or the 2 mm wavelength. Whereas for centimeter wavelengths used for the precipitation radars. Okay, so electromagnetic waves and these fundamentals I'm skipping. So because the main thing, so this is the important thing. So usually radar frequencies divided in broadly into a VLF, very low frequency, that is 3 to 30 kilohertz, whereas this one is in a wavelength in kilometers or meters, but we won't use this one. Giant means one is our Pune University, there is a giant wavelength radio telescope, it is there. They use somewhere in this frequency, whereas we uses very high frequency. This is what MST radar or the NMRF they are using. There is a 53 megahertz they use. 6 meters wavelength is the thing which is used for the wind profiling and stratosphere, mesosphere, ionosphere, and tropospheric study purpose and their winds. And UHF radar is the boundary layer radar. So this usually having a 20 centimeter to 10 centimeter wavelength radars, whereas SHF super high frequency and extra high frequency. These are the actually weather radars. So this is separately I am bringing here from 1 mega. So for example, 1 to 2 megahertz is called the L band radar. 2 to 4 is the S band. 4 to 8 it's almost doubling. 4 to 8 is the C band, and 8 to 12 is the X band radar. L, S, C, X, and Ka band. So remaining two we won't use because they attenuate very quickly. So that's why most of the precipitation radars exist at S band or C band or X band, whereas cloud radars exist either at a K band, which is 34 gigahertz, or a W band at 94 gigahertz. Remaining have their own significance, but for weather radars we use this only: W band, K band, X band, C band, and S band. For example, from top to bottom when you are coming, their wavelengths are reducing. So that means they are very sensitive for the SCX. From top to bottom when you come, they are very sensitive for the cloud droplet. That sensitivity itself is a sin for that particular radar, because it will enter into the, that my scattering is a wavelength. For example, S band, if you take, it is a 3 centimeter wavelength. That means a moderate rain when it comes, it started entering into the my scattering. Whereas S band, even complete, we know that the bigger size of the rain droplet is a 6 millimeter. So its wavelength is a 10 centimeter wavelength. So it is very safe. Even as 6 mm bigger drop size is existing in your rain, so it is very robust. It is less sensitive, but it is robust. Whereas X band is very sensitive, that itself, because it is a 3 centimeter wavelength, so it is having a chance to, when it is a 4 mm wavelength, 4 mm or 5 mm drops are coming, they are closer to the entering into a my scattering fields. Whereas K band is not good for at all rainy condition. It's good for a cloud droplets. So cloud droplet we learned yesterday, like a 10 mm to something like a 400 mm. So that's why cloud radars are better, either K band or W band. So these are the different wavelengths we are using, because not a single wavelength used for the all types of weather events. Because if it is a hail, even S band can get some problem, because hail will be something like 10 mm to 50 mm or like that. So but because its wavelength itself is a 10 centimeter, so if it is less than, it should be lambda by 10 times, then only it is Rayleigh scattering applies. Okay, so now we will see in the next. So let us see the basic working principle of a radar. Yesterday I told, because I don't have this presentation animation, a transmitter, because it's have its own power source. That's why it is called a active remote sensing agent radar. So the transmitter is have its own power, and the transmitter is connected to the antenna through a circulator or a duplexer, and where we will tap the energy which is returned from the antenna when it's in a receiving mode. It will be connected this one. This blue one is active to this part, and this one is connected to the receiver. So transmitter, receiver, and an antenna with a circulator or a duplexer at this point is called the antenna block diagram. Whereas the antenna is the intercepting part between the electronic part of the radar to the environment. Okay, so it is a transducer. It converts the electronic signals into a air propagating, means in the air it will send that it radiates the energy and it enters into the free space propagation. It will happen through antenna. So while it's transmitting, just you see this animation, I'm just switching on the radar. Just you see, there is a red signal or a pulse has gone and hit the target at a particular distance, and when the target it hits this energy, it has re-radiated the energy in all direction. That means it intercepts the small portion of the transmitting energy and it has gone forward. So that means your target is much smaller than the probing wavelength. That's why it is intercepted and it scatters the energy in all direction. However, the energy which came back where it is originated, it hits back also. Let us see once again. We'll go back. I'm switching on. Just see very carefully. So the signal has came and it hits the thing, and this black, that means this is a back scattering in the direction of the antenna. So when it came, then this will be connected back to the duplexer, and duplexer now provides a lot of conductivity in this direction and insulation to the transmitter. So the energy which is coming, which is very small, like in a 10 to the power of minus 9 to 10 to the power of minus 12. So the difference between the transmitting power to the receiving power, transmission may be in 1 kilowatt, 10 to the power of 3, and coming is 10 to the power of minus 12. So the total difference is 10 to the power of 15. So that is the difference between the transmitting and receiving energy. So the received signal is very weak, very feeble. So that particular energy, okay, so the receiver should be sensitive for that much amount of signal, that much feeble signal it is sensitive. Whereas a transmitter is 10 to the power of 3. Why I have to provide a relay here? So transmitting powers are in kilowatts. If this power is even a small leakage entering into a receiver will burns out. That's why this particular duplexer is acting like a conducting path in while it is transmitting. It connects the transmitter antenna to the transmitter, whereas this particular thing provide a high impedance to the transmitter while it is receiving, and only enter that small energy to the receiver which is very sensitive, and it process further to the target detection and extract the information about this target. Let us see once again. I'm switching on and it has gone, and the radar wavelength is so big, so only the small amount of energy it intercepted and it is returned back and entered into the receiver. Using this cartoon, I'm going to explain the radar equation. So, do you got this particular point, all of you?
Yes,
Please
sir.
know.
Yes, sir.
So this is the thing. If you have any doubt, call me, because I'm going to use each step that is like this. So transmitter on. So that means antenna, when it's a transmitting, I use the gain. While it is a receiving, I use the aperture of the antenna. That means while coming, how much bigger is my antenna size, physical size, that much is the better that all this scattered energy, it will be intercepted by this physical aperture of the antenna while it is receiving, whereas transmitting, its gain is important. So these are the things which I introduce as and when I convenient to explain the radar equation. Okay, and one more concept yesterday I explained, C into tau p, that is the pulse width of the wavelength. So for example, 1 microsecond and 3 into 10 to the power of 8, that is a 300 divided by 2, you will get the range. I told yesterday resolution also, because I use a T pulse width. Now I am using the TIPP, interpulse period. That means one transmitting pulse to the, I told it is a transmitter on and transmitter off. Again, I will transmit on. So that means one transmitter on and one transmitter off is called the interpulse period. That means the one pulse to the next pulse in between the gap is also I will consider for all the receiving purpose. So that is why C into tau p, it is called the interpulse period. That means 1 microsecond, for example, I transmitted, and 999 microseconds I waited for the receiving purpose, for example. That means 999 plus 1 microsecond. Total is 1000 microseconds. If it is 1000 microseconds, if I keep, how much distance it is propagated? For example, 150 into 1000. How much? 1 microsecond is the 150 meter resolution. I already explained. Into 1000 I am doing now. That means 150 kilometers, right? Do you agree?
Yes, sir.
So if you use a interpulse period of 1000 microseconds, so my radar essentially can listen as farthest distance is 150 kilometers से signal आने तक वो wait करता है. Then I transmitted another pulse. Okay, so that is the radar wavefront looks. Okay, so this is the basic principle. And for the location, for the target location के लिए मैं beam width concept use कर रहा हूँ. That means if the antenna is bigger, then the beam width is very narrow. It is like this. When the beam is rotating from a position 1 and position 2 and position 3, can we come back again? Now beam is formed. Okay, let us see. So the target location, when a beam I am kept in a one position, that means, and the second position, when beam is I am rotating by a scanning radar, when I am rotating in a azimuth or elevation, so I can point a target very closely. For example, the target is at second position. Exactly when it comes to the second position, you will receive a maximum energy. So this way, correct location can be done. That means a beam concept helps you to how you are able to locating using a azimuth and elevation angle changing. You are correctly pointing exactly to the center of the beam the target lies. So that is the way. So we are locating. Okay, for this purpose, that means this purpose I use a antenna is called a directional antenna. For example, antennas are two types. Omni antenna, that means it can direct the signal in all, it can disperse the signal in all directions, similar to a target. When the target is backscattering the small amount of energy, it is re-radiating in all directions. So our target works as a, our target when it is hit by energy, it works as a, it transmits in all directions. So that is called, works as a omni antenna. So that means this directional antenna, that is a parabolic antenna, if I remove and I keep a small wire, so it can emit the energy in all direction, equal amount of energy. But that way, you cannot able to focus all the energy into a beam. So for that, a parabolic antenna can bring all the energy into a particular focused direction that will help to illuminate the target much better way. So that is the reason we have to use a directional antenna. So that we are going to, so these are the another type. This is a monostatic antenna, uses a same antenna for the transmitting and receiving purpose, whereas a bistatic radar, bistatic means a transmitter having a same antenna and the similar features of the antenna has to be used for the receiver. So here pulsed energy is not required. The continuous energy is enough. That means a transmitter is continuously transmit, whereas a receiver continuously receive, because they have different antennas for their purposes. But usually antennas are very costly, especially as weather radars. A very polished antenna will be takes the off of the cost of the radar. That's why if you are time multiplexed, that means sometime you use for the transmitting purpose and sometime the same antenna used for the receiving purpose with a circulator or a duplexer in between. That is called a monostatic antenna. So most of our pulsed radars is automatically can tell as a monostatic radars.
Sir,
Whereas in the
what is the
bistatic
difference between modulator and duplexer?
pardon?
Duplexer and modulator, what is the difference?
Is a modulator is for the modulating purpose. For example, if you are sending a amplitude modulation or a frequency modulation or a pulse shift width modulation. So, for example, I want to say this way: if you have a paper, right?
Yes, sir.
So you want to give it to your friend, you can just hand over to his hand, right?
Right.
But in the that is called the means conduction convection radiation. Have you heard about?
No, sir.
The energy, if you want to send anything energy to a long distance or to a next person, you will either conduction. That means you take a iron rod and keep in the heat. So that means you feel the heat after some time to the other end, right? So that means the energy is vibrational energy due to the heating is slowly percolate because of a conducting media. It transmits from one molecule to the another molecule by vibration. It comes to the other end. That is called conduction. Whereas a convection is nothing but it is for example, you are heating the beaker of a water on a stove. The first layer close it to the flame. It heats up. That layer slowly full layer of the heated layer will be slowly transmitted to the upper portion of the beaker, whereas the colder water will come down. So this is called convection. Okay, convection is nothing but a group of atoms or the group of heated particles will shift to the upper thing. See, it's called a plume. So plume concept as well. Whereas radiation, that means energy is radiated in a free space. So this radar also having radiating the energy in a directive antenna. That's why this is coming. So now you are asking a duplexer, right?
Yes, sir.
Sir, what is that modulator purpose?
Yeah, modulating is nothing but, for example, if you want to send your audio wave or a video energy into a long distance, you have to use a carrier frequency. That means your means whatever I am talking, that is called the information signal. Okay, which is not having a lot. If it is an audio signal, it can immediately attenuates in the atmosphere. Maybe after a 10-15 meters के बाद कुछ भी उसका energy नहीं होता है. For example, if it is a radio wave, it can propagate to up to thousands of kilometers, even from here to moon. But for that, you have to put in a high energy carrier source. That means it has to be kept in a carrier. For that example is that a paper, if I asked a very strong person, means energetic person, to throw from maybe IITM building to a Prithvi, okay, how he can throw that paper? So common sense is that he can wrap into maybe in a stone, he can throw maybe to the outside, other side of the road. That means a stone is a carrier. It can passes this paper to other sides. Similar way, your audio energy attenuates very quickly in the normal atmosphere. It has to be modulated. It has to be modulated into a amplitude, either amplitude modulation, phase modulation, or a frequency modulation. It has to be done. So these are the modulation things which a radio, for example, your earlier before TVs there are radios, right?
Right.
Yes.
You used to listen at different frequencies, different things. So what they used to tell, it is transmitting in the FM. Today also it is there, Radio Mirchi, right? So they used to tell a frequency,
Yeah,
14.7 FM they used to tell. So that is called frequency modulation. and another one is amplitude mod. These all modulations are used for the sending the your information signal, which is very weak, to a longer distance by modulating it with a higher carrier frequency. This is the electronics part. If somebody is having electronics background, they might have learned this. Otherwise, you just feel that if you want to send a energy for a long distance, modulation is required. For that, modulator will be used. Understand?
Yes, sir.
Okay. So,
Sir, the purpose of modulator is to switch transmitter on and off in simple words, right?
no. Your
I
transmitting
read that.
signal, for example, I am using a S-band radar, that is 10 centimeter wavelength or maybe 2.5 gigahertz frequency. Okay, this 2.5 gigahertz frequency will be modulated with a maybe a 50 megahertz or a 100 megahertz frequency.
Okay.
Okay, hello.
Okay. Yeah. Yes, sir.
So the higher this particular frequency can be converted into intermediate frequency, then it is converted into a very high frequency, because in the carrier frequency, for example, I want to send a food to you. So what I will do, I will make a carriage, right?
Yes.
Carriage में लगा कर भेजता हूँ, right to you.
Yes.
There you will open the carriage and take your food. Similar way, information signal will be kept in a carrier and sent to a long distance. From there, I will keep a demodulator and it opens the carrier wave, and from there, information signal will be demodulated, and that I will be using for my information extraction. Do you understand the concept?
Yes, sir.
Is it clear? For example, you want to eat a food, but this food is made at maybe IITM canteen, and it has to send to you. I cannot just throw the food to you. What I will do, I will pack it into a carrier, that means carriage or a box. After coming to you, what you will open? You will open the carriage and you will take the only food, not the carriage. Carriage is just a means to get the food to you, right?
Right.
Similar way, when I want to send a information signal which is very feeble or which is very chance to get attenuate in the atmosphere because of rain and all these things, because of various factors, so it has to be packed. So it will be packed by a modulation, whether it is a frequency modulation, whether it's a amplitude modulation, or maybe amplitude modulation or phase shift key modulation. So after this modulation, it is very safeguarded in that carrier wave, and it will propagate because it is a highly energetic carrier is a highly energetic signal. So on each, it is modulated and it will transmitted in the atmosphere. After going to a destiny where the demodulation will happen, and it takes the information signal and throw the carrier. That is the purpose. Is it clear to all of you?
Yes, sir.
So that is the purpose. So when I made, so this is the monostatic antenna I am going to use for all my weather radar probing purpose. Okay, bistatic is more, the example of bistatic is the in between these two antenna the road is passing, that means highway. So one side of the road I will keep a transmitter, other side of the road I will keep a receiver, but in the center I am going with my truck with a very high speed, for example. So transmitter signal will be objected for a small time, so that by that time the receiver will be blocked for the objection. So by that, how much speed, that means how long the objection is happened through receiver, I can calculate the speed of the truck. So this is the, yesterday I told the traffic purpose they use. So there bistatic concept of radar will be used. Okay. Now I am going to come to the radar equation. The radar equation relates the, so if anybody asks, can you explain the radar equation and tell about the characteristics of the various components of the radar? So radar equation relates the range of the radar, that means what is the maximum range of the radar it can detect the weakest signal, to characteristics of, by the characteristics of the transmitter, that is this green, and receiver blue, and an antenna and a target. Are you getting my pointer? Could you able to see?
Yes, sir.
So this is the target, this is the antenna,
Yes, sir.
and this is a transmitter, and this is a receiver. So there are 4 functions are there. One is a transmitter, another is a receiver, and third is the antenna, and fourth is the target, and fifth is invisibly environment. That means from antenna to target in बीच में जो भी होता है वो तो environment है. वो dry भी हो सकता है, wet भी हो सकता है. Dry मतलब means there is no raining, clear air conducting. When there is a raining or snow or fog something, then the environment is affected by the environment. So there are 4 physically seen, 5th one is the environment. So whatever I am using this block diagram, same thing I used for the radar equation. That's why if you remember this block diagram image, you can write the radar equation very easily, and you can define the radar equation also. The radar equation relates these 5 parts. If you write in this way, so your image will be converted into a information. The radar equation relates the range of the radar. So remember, range is the means LHS. That means in the radar equation, I will keep the range in one side, all other components in the other side. Just see the next slide. Okay. So this is, before I explain, actual radar looks like this. This is another block diagram. This is the antenna, and this is a feed. Yesterday I explained, and this particular curvature is called the reflector, which makes the total antenna is a directional antenna. It is called reflector, and feed is the thing which either means the source of energy. I told the source of energy, it will come here and it radiates the energy onto this reflector. Then from where the parallel wave will come. Okay, and the transmitter is here and the receiver is here, but transmitter is helped by the modulator. Somebody asked about the modulator. This is the function of the modulator. What it will do, it generates a high frequency carrier wave that will be mixed with a transmitting information signal, and it makes a ready to radiate through antenna, through a duplexer or a circulator. This circulator, that means a round part is there, which is the in between the transmitter and receiver के बीच में होता है करके मैं बताया ना. This is called circulator array duplexer, which provides which provide a conducting path to transmitter and antenna one time. That means when pulse is on. When pulse is off, that means when a pulsed signal, pulsed antenna is there. Sorry, pulsed radar is there. So one pulse when it is transmitter is sending, that time this transmitter and antenna will be conducting path, whereas receiver is insulating path. That means no energy leaked to the receiver. And when the antenna is transmitted into the atmosphere, it waits for the 999 microseconds for receiving up to 150 kilometers. So all the energy in the 150 kilometers will be received in 999 microseconds time. And that energy, during that time, this antenna and receiver is a conducting path. That energy goes into the receiver, where it will be mixer is there. So what it mixes is, whatever the modulator carrier frequency is there, that will be resonated. That means it is mixed with that signal, so that the returned path carrier energy is decoded, and only information signal IF, that is intermediate frequency, will come here. That intermediate frequency will be connected to the either reflectivity or a velocity. If you want a velocity, the same IF energy can be phase decoded. That means the phase of the amplitude is the reflectivity, whereas the phase information will have the velocity information. Because you know that what is Doppler is rate of change of phase. Okay. So for example, in any signal, for example, I want to take, this is the signal, the red part. So the peak to peak signal of this one is called the amplitude, whereas the phase information of this signal will be used for the velocity finding purpose. You understand?
Yes,
Up to
sir.
here?
Yeah.
Yeah, because you are not an electronic student, which that's why I'm not explaining the what is shallow. This is called the stable oscillator, which will be used to get the exact information. Means the stable oscillator will be linked with the high carrier frequency. Then it is attached to the modulator. So that is the carrier frequency modulates and go out. Whereas receiving time, same carrier frequency information will come back with a small amount of energy, means very feeble energy, that is demodulated with the carrier frequency and get the information frequency. That information frequency amplitude used for the reflectivity calculation, reflectivity computation, whereas its phase used for the velocity computations of the target.
Sir, Neelam is the electronic student.
Pardon?
Neelam is the electronic student.
Oh, Neelam can understand this, I think so.
Yes, sir. Yes, yes.
Excellent. Because we have only 2 classes, that's why I am not carrier. But if it is a specified radar meteorology things, I would have taken a 1 class completely for it. Okay, now I'm coming to a simple radar equation. Why we have to, first of all, why this radar equation is required? Because we are all fearing about mathematics, but sometimes mathematics is the mother of science, mother of all sciences, for example. So it can give a clarity very quickly. So that's what I'm going to ask you, that don't fear, but we love the physics or a science of it. Just see which is no complexity, because you already have a image, you already have a block diagram of radar, and radar equation which I already told, just I kept it here, I just pasted here. Radar equation relates the range of the radar to a characteristic of a transmitter, receiver, antenna, target, and environment. 5 things. That means your handful of fingers, if you remember, the radar equation can be told. But simple radar equation, what is the, why I told a simple radar equation? A radar equation is the heart for the understanding the complete radar textbook, because everything orient to these all 5 things. A simple radar equation can help you to design a radar and understand the radar characteristics of the each part, like a transmitter, receiver, antenna, target, and environment. And simple radar equation can also be helpful to you to not only the designing, but also verifying that uh, each function of transmitter, receiver, antenna, target, and environment, and also their losses associated mainly with the antenna, radar, and environment. And target characterization is the important thing, because its range is very important. So one thing I want to take you attention now, the range of the radar, if I want to find, first of all you should know one thing, how much power I am transmitting, okay, and in which way I am transmitting. For example, I already told, when transmitter switched on, that means it is connected, the transmitter electronics part is connected to the antenna, which converts the electronic signal into a radiation. It radiates the electronic energy into free space in the atmosphere, right? So for that, I am assuming not a directional antenna, where I have shown in my cartoon earlier. First of all, I will use a isotropic antenna. What you mean of isotropic antenna is a antenna which can radiate the energy in all direction equally. Okay, the power density at a range R, you see R, range of the radar find out करने के लिए मैं पहले से अभी आपको prepare कर रहा हूँ एक equation. What is the range of the power density by an isotropic antenna? So that means PT is the transmitting power. Okay, so I just want to call you your 10th class or the intermediate physics. Okay, so there you might have seen the 2 charged particles, if they are separated by a distance r. Coulomb's law. Do you know this? Coulomb's law?
Coulomb's law. Coulomb's law, yes.
Yes, sir.
So where what we will use, if you remember vaguely, so if it is a 2 particles are separated by r, what we will write, that particles may be, if it is a p1 and p2 by
4 pi r square.
Yes, that 4 pi, how it came? Can you tell that? because it's a spherical, right?
Yes, sir. Area.
Yeah, area 4 pi r square, right?
Yeah.
So that is the thing. So if you recollect the Coulomb's law, that transmitting power divided by 4 pi r square, but it is by a isotropic antenna. Remember, this is a power density at a distance r. So that is proportional to inversely proportional to 1 by r square. That is what we learned the electronics part in Coulomb's law.
Yes.
So now we will come to the what happened? What's the next slide? Yeah. Okay. So if I use but you have seen in my picture a directional antenna I used. That means all the energy not transmitting in 360 degrees around it, but in a particular direction. That means a parabolic antenna I use, all the energy by a field I am throwing onto a reflector, and reflector energy comes like a parallel beam and it will go into the space. So for a directive antenna if I use, then a gain of G will be multiplied with a isotropic antenna because it is a directional antenna. Now all energy I am not transmitting in all directions around me. I am transmitting only to a particular in 1 degree instead of 3 degrees. I am bringing all the energy into a particular position, particular 1 degree position, so that it forms like a small beam. For example, in a night when you are going in a train in a very dark, somebody uses a torchlight, you can see like a beam, right?
Yes, sir.
If you use in a morning, you cannot see it's like a beam, but if it is a dark, you can see like a beam. Similar way, when you use a directional antenna, so that means a reflector, it provides a gain of G. Okay, Pt G by 4 pi r square. So that means the step number 2 for the radar equation you already got. That means first of all you have to use a isotropic antenna and what could be the power density at a distance r. And next is a directional antenna. For directional antenna, gain will come into picture. That should be multiplied. Multiplication will happen. Okay. Then next, the gain. What is the gain? Is gain of an antenna is a measure of the increased power density in a particular direction as compared to the power density that would appear in the direction from an isotropic antenna, which I already explained to you.
Yes.
So it is the gain definition is like this. Can I proceed?
Yes, sir.
Yes,
Okay.
sir.
Now, for example, now I already switched on the transmitter. एक wave आ गया बाहर and उसका directional antenna का भी part में ले लिया. Now it is going towards the where it is going. It is going in a direction where the target is existing, right? So now the target sigma, for example, when the energy is intercepted by a target have its own physical size, right?
Yeah.
So that is called, for example, sigma is its size. Okay, how much it is re-radiate back, because again it is working like a power density. It is also re-radiating back, right? So then what you have to its physical size, because it is not transmitting its own.
Yes.
You understand? It is a
Yeah.
passive sensor. Passive target is a passive, but it uses the source energy of the radar. It uses that energy and it intercepts small portion of its energy. How much it intercepts? It is a intercept a sigma of. That means it's of its own size and its shape. Because of its shape and size, it get a means radar cross section. The sigma is called the radar cross section. So radar cross section divided by 4 pi r square is the amount of energy it re-radiates back. So 4 pi r square कैसा आ गया आपको ऑलरेडी मालूम है. ओनली सिग्मा का आपको मालूम होना चाहिए, क्योंकि मैं तो टारगेट का इक्वेशन में लाना चाहता हूँ. ठीक है, रडार इक्वेशन में सब फिजिक्स. नाउ दैट्स इफ यू रिमेंबर दैट अर्लियर इमेज व्हाट आई हैव गिवन, द टारगेट को मैंने क्या नाम दिया, अर्लियर में टारगेट नाम दिया, इन दिस इक्वेशन में सिग्मा दिया रहता हूँ. सिग्मा का नाम क्या है? रडार क्रॉस सेक्शन. ठीक है, radar cross section is a measure of a target's ability. That means It should be what we learned in the radar definition. Radar is a electromagnetic system for the. Can anybody tell the radar definition? Yesterday.
Yes, sir.
Can you please tell me yesterday 2 lines of the radar definition?
It is an electromagnetic system. One second, sir. Hello.
By using
yes.
electromagnetic energy to detect the shape or
To
the
locate
signal
a
For detection
to
and
locate the
location of reflecting object or target.
right here. So that is a reflecting agent होना चाहिए. Target का property क्या होना चाहिए?
Reflecting
It
agent.
should reflect, or it should
Reflect.
reflect. It is not a normal target. It is a means back scattered power, means इसको back scattering करना चाहिए. For example, if it is transmitting to that wave, it will allow it to pass through it. It cannot intercept any energy. So such things will not be a target for us. It should intercept. That means reflect the radar signal in a direction of the radar receiver. Okay, so that means it has a property of a reflect करना चाहिए. थोड़ा तो reflect करना चाहिए. वही target की काम करता है. ठीक है? So that is what is the radar cross section sigma. That means target का नाम है मेरा ये equation में sigma, but 4 pi r square क्यों आया? Because it is isotropically transmitting the scattered energy. Okay, just you see back what is happened here. So when I switch on, it is radiated in all direction and one energy came to antenna back, right?
Right.
You got it? So that's why now the third step is the target part. First step is the isotropic antenna, second step is the directional antenna, third step is the re-radiated energy back to the signal. That small black signal came back to the antenna. Now when it came back, so this up to 1.3 आपको समझ में आ गया. radar equation के ऊपर आपको डर नहीं है, but आपका पीछे एक knowledge है. That means एक image है आपके पीछे, इसीलिए आपको equation कुछ डर नहीं देगा, because इसके पीछे का knowledge आपको मालूम है. Now I want to introduce the concept of, means I told when it is a receiving time, how much bigger is the antenna, that much it is the grade of that particular radar. जितना बड़ा होता है उतना अच्छा होगा, because AE, I want to use AE. Now the multiplication of AE is the receiving part. So that means it is called effective aperture of the antenna. Will be that much energy will be captured by the antenna. That's why AE I have to add. Well, similar way when I'm transmitting G I have used. That means gain of the antenna is in the transmitting time, it is very useful parameter, because that much gain, all 360 degrees I brought into 1 degree. That means I gained by 359 parts, came into a particular direction, right? That is why I have to use a gain in the directional antenna, whereas in the receiving part, same antennas, physical aperture is very important. That is called AE, is nothing but a effective aperture. That means even if physically it is so big, but if it is not nicely polished, the antenna is not nicely polished, that will not be directed towards your feed. Antenna के एक feed होता है, मैं बोला है ना, वो feed के पास ये energy collimate होना चाहिए. That means that all things should be converged towards the फीड के पास होता है तो ही इलेक्ट्रॉनिक्स के, दैट मींस रिसीवर के पास चली जाता है. इसके लिए आपका एंटीना को फाइनेस्ट पॉलिश होना चाहिए था. इफ इट इज एंटीना इज, ये पॉलिश करने के लिए इसका कॉस्ट बहुत बढ़ जाता है. फॉर एग्जांपल एंटीना डिजाइनिंग इज ए रियली आर्ट. इफ योर हाईली पॉलिश्ड एंटीना इज देयर, दैट मींस व्हाटएवर इट टचेस इट गोज टू द सेंटर ऑफ इट एंड फीड में चली जाता है. फीड इमीडिएटली कनेक्ट टू द your receiver part, first part of the receiver, that is called the low noise amplifier. Then it amplifies it, and maybe 1000 times or 10,000 times it amplifies, and it connected to the next level, that is a decoder. So there It will be extract the information signal and try to understand the signal. Here I want to tell a small story. For example, today I brought a आटा लाया था मेरा घर में. Okay, means shop से. Then after some time I got a I want to tell you that what is happened at the receiver when the information signal is received. So how to characterize the received signal to get the information out of it, this story will tell. For example, if I bought a rice or maybe atta, so my wife or my mother made either chapati or a samosa or maybe some other pudding or maybe some other thing, then I can understand that what she would have make use of this particular, I brought it from the market, she has processed it, right? She has processed and made a particular item out of it. So similar way, when the information signal, when it is received at the receiver, it should be analyzed. When you analyze, by analyzing it, you can know that what happened in the atmosphere and what is the, means you can characterize the targets. Similar way, for example, when I gone and she made some samosa, then I can analyze that she might have आटा को चपाती का means duff बनाया and उसके बाद चपाती बनाया and it has to be gone into a next level, means I can know all the process what is happened. Similar way, when the signal is gone into a rain, so if it is a rain, so signal will have some signature of it. If it is a aerosol particle, it have some other signature. If it is having a cloud, it have a other signature. And if it is a birds or insects, it is having a other signature. That means whatever the received signal, so after analyzing, you can able to know that whether it is gone through a rain media, whether it is gone to a cloud media, whether it is gone to aerosol media, or whether it is gone to a clear no media at all. That means just free air, and it is gone to a fog, or it is gone to a insects or birds, some non-meteorological things is affected. All these things after analyzing it will be known. That means signal processing is the important step. Okay. So of course I just want to give that information. Now while it is receiving, AE is multiplied. AE is nothing but a effective aperture. Effective aperture is related to the physical aperture. Okay, by this way. Here I have not given the equation. Okay, so maybe somewhere I might have given just here. Okay. Yeah, effective aperture. Hello, effective aperture is related to the gain like this. G is 4 pi AE by lambda square. Okay, I will come back. Yeah, here, so the for example, the re-radiate energy is came like this. Now I want to use the aperture of the antenna AE. This is called a received power. That means a received power is equal to PTG sigma AE by 4 pi r square whole power 4. That means 4 pi square r power 4. So we almost done the radar equation up to here. So PT is the transmitting power, G is the gain of the antenna, AE is the effective aperture of the physical size of the antenna, and sigma. So here I am using AE and there is a AP. AP is nothing but a physical aperture and AE is nothing but a effective aperture. Because I told that even the physical aperture is size is whatever you are seeing with your naked eye is a big size, but if it is not properly polished, that means if it is efficiency of an antenna is not 100%, under the ideal condition, AE is equal to, okay, rho into AP hota hai, where rho is called the efficiency. If it is a 0.5, that means 50% efficient antenna it is. That means जो आप physically देख रहे हैं, वो physically part is not really helping. Only 50% of his physical size is collimating towards the focal point. For example, if it is an ideal antenna, highly polished and ideal antenna, maybe it is having a 0.8 or 0.89 something. It never be 100%. That is the equation between the AE and AP. AE is equal to rho into AP, where rho is the fraction. It will be from 0 to 1. Okay, if it is a 1, it is a perfect antenna. The physical size itself is a effective size. That means the antenna is highly made, but if you want to made, you have to use a crores of rupees you have to pay for that antenna. Okay, so that is the AE. So this is PR. Now you see PR received power. That means whatever the receiving power is a function of directly proportional to transmitting power, gain, effective aperture, and backscattered. That means size of the target divided by 4 pi square r power 4. So this is called the point target. But I started with the range of the radar. So that means R max is equal to S minimum होना चाहिए. That means PR को S minimum जैसा मैं लेता हूँ. That means the maximum distance which I can detect with a feeble energy coming from a farthest point of the radar, that is 150 kilometers I told earlier. So उधर से कितना weakest signal आता है उसको मैं PR को S minima करके देखता हूँ. R max is equal to PT J AE sigma by 4 pi square or PR or S minima whole power 1 by 4. This is called radar equation 1.5. Is there any doubt now?
No, sir.
No, sir.
So R max is equal to is a function of PT J AE sigma by 4 pi R square into PR लिख सकता है, S minima लिख सकता है, because if you make R is equal to R max, then PR is equal to S minima हो जाता है. That means the minimum detectable signal at a maximum range is called the radar equation. Do you understand? This is called point radar equation or hard target equation or simple radar equation, with which we can able to characterize all these parameters. Before I'm going to switching over to a means distributed target, I want to take a one moment to tell the RCS, the radar cross section, is a measure of target's ability to reflect or scatter a radar signal in a direction of the radar receiver. That is called backscattered power per steradian. Because it is a cone beam is coming back. Because beam concept में आपको steradian use करता है towards a radar. Okay, here I explained this part, right? This linear part is called the up to A.
Aren't we considering it as cylindrical shape?
Not cylindrical, cone shape.
Okay. In some equation we use
for example,
cylindrical.
आपने पल्ली कहता है ना, पल्ली कहता है ये कोन में लगा कर देता है, right?
Yeah.
So that is called a cone. So that kind of beam will happen. That's why there is a steradian बोलता है उसको. Just if it is a two-dimensional, you will use a angle. If it is a three-dimensional cone, we will call a steradian.
Yes,
right?
Sir. Yeah, that is.
Okay. Now, when 2 pi r by lambda को मैं क्या बोला था? Size parameter. Right?
Right.
And sigma को क्या बोला था? Sigma by pi r square. Pi r square is called the physical size. And sigma is called the radar cross section. Radar cross section divided by physical size, which will be in the form of 1, 10, 0.1 in a log scale में होता है. And x-axis is the size parameter. If size parameter is 1, and if it is a physical size equivalent to the actual size, I mean electronic size, that is called 1. So that point is called A. So A to 0, that means origin, is called the Rayleigh scattering part. Rayleigh approximation or Rayleigh region, where the size, that means the size of the particle, if it is getting bigger, you will get a bigger returns. Okay, that is called the Rayleigh region. Most of the centimeter wavelength radars or all radars works in the Rayleigh scattering region. Whereas when radar wavelength is near equivalent to the my scattering, you will get a maximum energy, but immediately after that, your forward scatter will get highly affected. So that is what, when you are increasing further bigger and bigger size, sometimes you will get a minima, sometimes you will get a maxima. This will continue for up to size parameter become 10 times. That there you are entering into a optical region or a geometrical region. So The geometric regions in the radar, the usefulness of the geometric region is that for calibration purpose, we select the such a target, something like a sphere or called a tetrahedral antenna. We will keep for the calibrating purpose. We will use this one. So optical size of thing. Whereas mice scattering is a unwanted or the things it immediately entering into a damping regions. So the mice scattering also we will encounter. For example, that depends upon the wavelength, because I told 2 pi r by lambda. That depends also the backscattering cross section. So this is the backscattering cross section to the particle size with respect to wavelength. You will form this this diagram. So where the diagram will have a 3 parts is Rayleigh scattering, mice scattering, and optical scattering. Optical scattering we will use for the calibration purpose. Mice scattering we will use for the encountering that what is the type of the target, whether the target is closer to the radar probing wavelength, then we will tell that mice scattering is happening, or otherwise if it is 10 times or 16 times smaller than the probing wavelength, we will call Rayleigh scattering region. In the Rayleigh scattering region, beauty is that it is a linear equation, so that you can keep this one very simply in a radar equation, so that you don't have any complexity. If you are entering after A, so you will have a non-linear equation. That means non-linearity coming. That's why it is unable to control. So that's why in the mice scattering, once you enter, you require some corrections, and that to be some extent, because your forward scattering is also affecting. So after this, I'm going to the very quickly. I'm going. So radar equation I explained, and each because I told radar equation में 5 का रोल होता है. एक ट्रांसमीटर का रोल है PT से वजह से होता है. That means your R max depends upon transmitting power. If you increase the more is the transmitting power, your maximum range can increase. Okay, and if you increase the gain, also maximum range can be increased. For example, somebody asks, if I want to observe up to 400 kilometers, that means what you have to do? You have to increase your transmitting power or antenna gain. Antenna gain कैसे increase होता है? If you increase the antenna size, your beam का size बहुत narrow हो जाता है. So बहुत narrow. For example, earlier I told 1 degree beam width. If I want to make a 0.1 degree, my gain will increase very big. So gain को increase करना है तो antenna का size बढ़ाना चाहिए. Antenna का size बढ़ता है तो AE भी increase होगा, but AE is nothing but a effective aperture. That means electrically कितना effective है. That means how much it is the polished. So AE, if it is AE is maybe 90% efficient, then also you will increase the maximum range. And sigma backscatter cross section. If you increase the backscatter cross section, R max can increase, but you may have a chance to entering into a mice scattering also. So some of the trade-offs are there. For example, if you goes on increasing your transmitting power, so there is a limit, because it can burns your systems. So that's why there is a limit on each one. So that limit, maybe if you in your advanced classes you can learn, but this is enough. So R max, that means range of the radar is a function of transmitter, receiver, and antenna physical size or effective size and a target. And one thing is missing in this radar equation is the environmental part. Other than that, everything came. That's why it is called simple radar equation. But to the power of R power 4. Okay, means R power 4 होता है तो ये सब होता है. That means R max is equal to all to the power of 1 by 4. This is called the point target or a hard target radar equation. Okay, इसको differently convert कर सकता है antenna parameters use कर. G and AE are connected by this equation. G and AE connected by 4 pi A by lambda square. If you put this radar equation is independent of the receiving antenna size. That is 1.7. 1.5 is a dependent on transmitter, receiver, antenna and target. But now I want to simplify this radar equation further. Now if you see 1.7, there is no AE. That means it is independent of the receiving antenna size. Now 1.8, there is no G because I converted everything into physical size of the antenna. So it is independent of the transmitting antenna gain, this particular equation, because I used this connection. Now the limitation of the simple radar equation, even radar equation used to characterize all the components associated to the radar. However, I have not used the environmental part, but the environmental part includes the noise or the attenuation. Those things I am bringing. Statistical nature of the minimum detectable signal. That means at a farthest distance I am getting a weakest signal. No? So that is called a minimum detectable signal. Is also having a problem with your receiver electronics, because receivers are made by the electronic particles. They have the noise because of the because of the background temperatures. So that receiver noises it will affect, but that is not there in the radar equation. Another one, fluctuation and uncertainty is associated with the backscattering cross section sigma. So that we have not. For example, my target is moving. That means in a different direction. It is not a spherical size. It is a, for example, aircraft. In an aircraft, different directions. That means it is in one direction you can see only the nose part. If you are just heading towards some aircraft is coming towards you, you can see only its head part. You cannot see its whole size. But if it is orthogonal to your head size, you can see a lot of lengthy airplane, right? So that indicates that its shape and size is very important towards the antenna direction. So that fluctuation and uncertainties in the target size and the loss experienced throughout the radar system. That means in radar, transmitter, receiver, all electronics, those part is not there in the radar equation. And finally, very important thing, medium ka, atmosphere ka, propagation effects due to the earth surface and atmosphere. So these are the things not taken care in this simple radar equation. These are the limitations. However, there is advantages of this one. In spite of the above things, but this simple radar equation is an important tool for assessing the performance of the radar. Because earlier I told transmitter power कितना हो सकता है तो मैं ज़्यादा distance देख सकता हूँ, and एंटीना साइज कितना होना चाहिए, एंटीना गेन कितना होना चाहिए, ये सब मैं डिक्टेट कर सकता हूँ मेरा मैक्सिमम रेंज कितना है. फॉर एग्जांपल व्हेन यू वांट टू डिजाइन ए रडार, टेक दिस सिंपल रडार इक्वेशन एंड वर्क आउट. यू कैन एबल टू design, but your wavelength should be fixed, because if you want to observe 400 kilometers, you have to select a S-band radar. If you want to observe a shortest precipitation radar, you may have to switch over to X-band, and if you want to cloud, you want to switch over the either 35 gigahertz or the W-band 95 gigahertz. So these are the knowledge you already having, because I have given a table for different wavelengths. What is the purpose I already told. So if somebody asks, please design a cloud radar with a maximum range of 45 kilometers. आपको डिजाइन करने के लिए कोई बोला है तो, or otherwise I want to observe a cloud within a 25 kilometers, then this radar equation will be helpful to you to design. Okay, determine the system trade-offs. That's what I told. Why I am telling only 20 or 30 kilometers per cloud radar, because it's a shortest wavelength. So the atmosphere in which it is passing, it will highly attenuated because of the gases existing in the atmosphere, or maybe rain or fog. So इसकी हिसाब से उसका maximum distance कितना होता है तो आपको अंदाज मिल जाता है. इसके trade off, determining the system trade off, that must be considered when designing a new radar system, and aid in generating the technical requirements for a new radar procurement. So this is the advantage of a simple radar equation. So do you have any doubts about the radar equation now?
No, sir.
No, sir.
Yeah. Now I want to switch over to a distributed target or a soft target or the weather targets radar equation. Only thing, I am just buying my last 1.7th equation, where AE is not there, but it is in the function of received power is directly proportional to G square. Okay, this equation I just observed here. From this, I am starting a further the radar equation for the atmospheric target. Here, I want to introduce say a volume concept. For example, I told my beam is a conical shape. Okay, in the cone, I want to a pulse width of 1 microsecond. That means the cone is divided into every 150 meters. So cone को एक 150 मीटर में डिवाइड होता है तो कैसा दिखेगा? एक two curved slant things will be there because it's a cone size. I cut into 150 meters width. So it will become like a not exactly a rectangular shape, but something like a means what I can say rectangle, but two sides are small slant parts, right? That is the volume of the antenna, the volume of the beam. That is defined by the finite pulse width and finite beam width. Because of beam width, the slant portions are coming. That means if I can draw, can I draw here? Let me see if I can draw paint. Could you see my paint now?
Yes, sir.
Could you see my paint?
Yes, sir.
Okay. Let me take a cone here. Where is the cone? Where is the cone? I can check cone.
It's in Word.
Pardon?
Word. Microsoft Word.
No, I want to do it here. Here also I can do
Yeah,
it.
you can do it, sir.
Madhu, take
Ah.
the pen and
Pardon?
take the pencil and write. You can't
Okay.
get it.
No, in this also it is there, yeah, somewhere.
No, we don't have that shape.
Late.
Otherwise, you go to the PowerPoint.
Yeah, it is here. It is here.
Okay, you want to take off.
Okay, so now I will cut this part. Oh, sorry. Oh. What is the
Shall I-
sound? Somebody is cooking
Shall I
also. Okay, this part I am taking and putting here, right? So this is the cone. It is not a three-dimensional, but now I will cut further into 150 meters. For example, this portion is the 150 meter, right? So this is the 150 meter things. Do you agree?
Yes, sir.
Okay.
Yes,
So
sir.
in this portion, either your cloud particles, millions of will be there. If it is a rain particles, maybe hundreds of will be there. In this particular 150 meter, that depends upon your pulse width. Because of pulse width, this particular things shame, and because of finite beam width, this cone shape has came. This finite beam width and finite pulse width, a volume will happen. So my only target is changing, right? So my target box scattering cross section को मैं क्या redefine कर रहा हूँ अभी? Sigma C is equal to VC into sigma I. This mathematical sigma I is called a digital integration. That means there are single particles, not a continuous media I am integrating. I am integrating each particle in the volume. They exist like a small water cloud droplets or a rain droplets. So sigma I into backscattering cross section of each weather particle. That is either a aerosol हो सकता है, cloud हो सकता है, or otherwise rain हो सकता है. So मैंने क्या concept लाया अभी? एक वॉल्यूम का कॉन्सेप्ट को आपको इंट्रोड्यूस किया earlier. A single target, that is aeroplane or missile or rocket or maybe a one vehicle on the road. So these are all the metallic target, bigger target, macroscopic targets. But now is a microscopic particles. Maybe within the volume there are million in the things. There are very small things, but their number density is very big. For example, a point target or a hard target equation, I am only looking for a single predetermined target. Either it is a enemy's airplane, or maybe a civilian aeroplane, or maybe a Scud or a target, anything. But when I am coming to a weather target, it's the sound from where it is coming. Okay, so the volume into integration of the backscattered part, sigma I. So this is integration of many small particles, backscattered particles is called, this particular portion is called the eta, that is called volume reflectivity. So radar reflectivity के पास मैं आपको लेकर आ रहा हूँ, वॉल्यूम रिफ्लेक्टिविटी को इंट्रोड्यूस किया, वॉल्यूम इनटू वॉल्यूम रिफ्लेक्टिविटी, VC into eta, where eta is integration of many small atmospheric targets backscattering cross section. So इधर सिग्मा C को सिग्मा I की तरह लाया, बट उसको एक V ऐड किया था. So eta is equal to sigma of sigma I divided by VC is called the, okay. Further the volume को मैं further characterize कर रहा हूँ because of the elliptical or spherical shape of a projected antenna area. So that is pi by 4. This is I have taken from the Skolnick. You can see this. So because I told already theta and means finite beam width and finite pulse width. I told the finite pulse width c tau by 2. This I already explained. C tau by 2 is a 150 meter resolution for 1 microsecond. That means transmitter का finite pulse width का information आ गया c tau by 2. Okay, now finite beam width को लेकर आना है, ये volume में लाना है तो, because I already showed this curved portion is due to the finite beam width and the top portion and bottom portion, that is for example red. Let me see. Where is the line portion? This is due to the finite pulse width. This red portion is. Are you getting?
No, sir.
Please say yes or no. Hello?
No,
Yes,
sir.
sir.
Yeah, this red portion, that means the top portion and below portion is the width of this red portion is defined by the pulse width, that is c tau by 2. That is c tau by 2. I am bringing the volume concept by radar pulse width and radar beam width, whereas the beam width concept is by the black lines. The black line portion is not exactly the rectangle, but it is a little curvature. So those things, because of its shape, pi by 4 things, that means pi by 4 things I am cutting. Understand?
Okay.
And 1 by 2 L and 2, that is the effective volume of a uniform rain illuminated two-way radar antenna pattern. If I want to consider, I have to use pi by 4 and 1 by 2 Ln by 2. One is because of the shape and another one is because of how much is the atmospheric target is filled in that portion, in that volume. So उसके लिए 2 log 2 1 by 2 Ln 2 लाया था. Now I have not explained for this r theta and r phi, because now I am showing in my picture. Here I am showing only 2-dimensional picture. But if it is a 3-dimensional picture, then you have to consider radar 360 degrees it is rotating, right? And also elevation. Because of if it is taken a cone, okay, cone में x-axis direction में जो angle होता है and y-axis direction में जो angle होता है, वो दोनों equal होता है तो वो perfect cone होता है. That means the cone end is circular. इधर जो top portion होता है ना, ये cone का end portion is circular. Are you agree with me?
Yes, sir.
So cone का end portion, if it is circular, what it means is it is x-axis if it is theta and y-axis is phi. Okay, that means it is in x direction and y direction is exactly the same. That means the perfect circle बनता है. That means your beam is perfectly circular. But sometimes elliptical beam form होता है. Elliptical beam में क्या होता है? Theta and phi are different. So if theta is equal to phi, then r square into theta square आ जाएगा. नहीं तो r theta into r phi, where r is the distance from the center of the antenna. So that is from here. That is, for example, this is the origin. ये कोन में ये origin होता है, तो this is the origin and this pulse I have taken maybe at a 1 kilometer के पास ये कट किया था मैं, ये जो मैंने कट किया था, तो मैं इसको ऊपर लाता हूं अभी. फॉर एग्जांपल ये पोर्शन इधर रखा है मैं. सो फ्रॉम ऑरिजिन से ये 1 किलोमीटर डिस्टेंस होता है, तो आई हैव टू पुट हियर 1 किलोमीटर. इन दिस पावर पॉइंट आई हैव टू कीप आर के जगह में कितना रखता है, तो बीम का कितना डिस्टेंस के पास आपने कैलकुलेट कर रहा है ये वॉल्यूम, सो उतना डिस्टेंस वो आर के पास रखना है. क्लियर? सो आर थीटा, आर फाई एंड सी टाउ, दैट मींस फाइनाइट बीम विड्थ को लेकर आया, फाइनाइट पल्स विड्थ को लेकर आया, एंड इसका शेप इंफॉर्मेशन एंड बीम फिलिंग फैक्टर. इफ यू ब्रिंग दैट फॉर्म्स ए वॉल्यूम. आर यू गेटिंग?
Yes, sir.
So volume into radar reflectivity, that means my soft target के इक्वेशन बन गया. बिकॉज सॉफ्ट टारगेट में क्या मैजिकल फिगर है, एक वॉल्यूम कॉन्सेप्ट को इंट्रोड्यूस कर ये 4 फैक्टर्स लेकर आना है. शेप एंड बीम फिलिंग फैक्टर, फाइनाइट पल्स विड्थ के इंफॉर्मेशन, फाइनाइट बीम विड्थ के इंफॉर्मेशन लाया तो ये सब हो जाएगा. नाउ यू जस्ट कीप इट इनटू द 1.7 में ये सब रख दो. If you put it back into the equation, this is called the distributed target. So point target में क्या होता है, बहुत बड़ा macroscopically very big macroscopically big things like a antenna, like a aeroplane or a scud or a means ship or a big, आप naked eye से देख पा रहे तो उसको देख पाएगा, उसको point target और a hard target की इक्वेशन यूज करना है. उसमें r power 4 होता है. pr is inversely proportional to r power 4, whereas here you see pr ऊपर मैंने एक बार डाला था. क्यों डाला है? बिकॉज here particles are very small. with a one pulse से आप उसको ऑब्जर्व नहीं कर पाएगा. you have to hit many pulses like a at least 10 to 100 pulses भेजता है, तो वो for example if it is a signal, all pulses if you integrate, the atmospheric target का signal integrate होकर increase होता है, whereas the noise decorrelate हो जाता है, because noise is always random in phase, whereas the signal is always maintains the phase. If it is a incoherent means maintains the phases, the amplitude will goes on add. If it is not maintains the phase, the phases will cancel out. That means amplitude, the signal coming from the first pulse to the next pulse, if it is coming from a target, it will be added. If it is coming from a noise, it will be decorrelated. That means it will be simplified. So that's why PR power sigma आया था, because it is integrated for the many pulses. It is called the incoherent integration. That means frequency domain integration or time domain integrations के हिसाब से ये हो जाता है. So इसकी वजह से sigma I, where means mathematical sigma I and cross section sigma I को मैं एक definition कर रहा हूँ in the next slide में, उसको Z करके. So then radar reflectivity factor को लेकर आ रहा हूँ. Okay, but before to that red things I brought it here because I told if it is a perfect cone, that means my cone का end size circular होना चाहिए था. So if it is a cone is complete circular, then theta and phi become same, that theta square by pi square आ जाता है. So pi square आ गया तो the radar equation will be simplified like this: PTJ sigma square C tau divided by 1029 ln 2 r square. Important thing is r square. That means a distributed target का equation PR is inversely proportional to r square into sigma I z. So this
Sir,
is
what happened to theta and this? They will be squared, right? If they are same.
Which one?
Go back, sir.
Yeah.
Back, yeah, that one. In the
Which
last
one?
formula 2.2, that theta b and theta phi b, they will be squared, right? Because
they are called theta square by pi square.
okay,
So theta square पे pi square को
okay,
मैंने 1 by g लिख सकता हूँ.
okay, yeah, right.
1 by g लिखता है तो g का स्क्वायर चली जाकर g में बैठ लेता है.
Yeah, because G is equal to pi square by theta b and phi b. Yes, sir.
Correct. That I already told here. G is equal to pi square by theta and phi b.
Yes, yes.
Okay. Okay. Now this is the radar equation, the 2.2. But it is usable thing is reflectivity करके मैं लेकर आता हूँ, because earlier sigma I is there. Sigma means mathematical sigma, integration of sigma, all small cloud droplets को मैं Rayleigh scattering का approximation लेकर आना चाहता हूँ. That is sigma I, each sigma I is equal to pi power 5 into the size, diameter of the that particle, either it is a cloud particle or a rain particle or a ice particle, divided by lambda power 4. So this is called Rayleigh approximation. Pi power 5 by lambda power 4 into di power 6 sigma I is proportional to, whereas the proportionality constant is a dielectric constant. For example, if it is a liquid, we use a 0.9. If it is a ice, I use a 0.2. Okay. So if it is a snow, I have to use 0.2. If it is a raining, I have to use a 0.9, because it is called the complex dielectric constant, because it's a real and complex things will be there. So that is eta minus 1 by eta plus 1, that is modulus k square, which is having a value of 0.9 or 0.1 according to the phase of the precipitation. So if I put this equation back into the 2.2, what I will get is PR, average of the PR is equal to pi power 5 by lambda square into blah 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 PTG C tau dielectric constant into sigma I into di power 6. So what I changed is backscattering cross section को मैं drop की तरह लेकर आया था, क्योंकि radar reflectivity is defined in the terms of how much rain droplets is existing in the radar volume. Okay, इसको earlier backscattering cross section की तरह रखा है, because if it is used for the either single point target or distributed target के लिए वो 2.2 equation तक use कर सकता है. But I want to use, especially for weather radars, I want to, because especially weather radars will only see the weather targets. It is aerosol or maybe a cloud particle or a rain particle. इसीलिए मैं इसी की तरह लेकर आना चाहता हूँ sigma I into di power 6. For this मैंने another magic use किया. First magic is the volume concept. Second magic is the Rayleigh scatterers.
What is D called? Dielectric constant.
Yeah, it's a dielectric constant.
And K?
Because water can exist in 3 phases. So you have to have a variability for that. If you have the variability, you will get like 0.9 to 0.2 change कर सकता है.
And K is called?
K is a dielectric constant. Complex dielectric constant means it is a complex. It is not a simple this one. It is a complex refractive index. Dielectric constant.
Okay, sir.
Okay. Right. Now the final equation is like this. PR is equal to something into dielectric constant into Z, where Z is called the refractive index, not refractive index, radar reflectivity factor. Okay, but the units of radar reflectivity factor is a very stunning, because mm power 6 means it measures in the units will be like this, power 6 into m cube. That means m cube already know because the volume concept की वजह से, but power 6 because di power 6 is there, where di is measured in millimeters. Are you getting?
Yes, sir.
Now I
Yes,
want to do a small exercise. When the radar reflectivity factor Z is power 6 by meter cube, for example, one drop size of 0.1 is there. That's what is my radar range. Radar range means rain range मैंने क्या दिया 0.1 mm to 6 mm दिया, but इधर मैं 0.1 से लेकर 10 mm ले लिया था आपको उसका effect दिखाने के लिए. For example, Z, if I place in the above equation Z is equal to sigma I into di power 6 में 0.1 रखा है. 0.1 power 10 to the power 6 को कैसा लिख सकते हैं? 10 to the power minus 6. Do you agree?
Yes.
So if it is a 10 to the power minus 6, I just multiply by 10 log 10. कितना हो जाता है?
Into log 10.
10.
Yeah. No. 10 to the power
Log 10 is 10.
No,
Log 10 is 1.
10 to the power minus 6 into log 10 कितना हो गया? Minus 6 आएगा.
Minus 6, yes.
Yes.
Okay, but I multiply with a 10 log 10, so minus 60 होगा.
Okay.
Do you agree?
Yeah.
Or shall I show on a screen?
No, it's okay.
Let me explain like this. So Control A, delete.
B raised for minus 6.
Okay. For example, 10 log base 10. Okay, 10 log base 10, 10 to the power of minus 6, right?
Yeah.
Do you agree? So this can be written as, oh sorry, I have to use the same, might be, okay, I'll bring it down. Okay, so this can be written as 10 into minus 6. Do you agree?
Yes, sir.
Yes, sir.
Okay, that is equal to minus 60. Do you agree?
Yeah.
So minus 60 dBg, minus 60 dBg corresponding to 0.1
1 Z.
0.1 mm rain droplet. So for example, if it is a 0.1 mm raindrop is there, only one raindrop is there in my radar volume, what I will get? Minus 60 dBg. For example, if I keep a 1, what I will get? For example, in the above equation, if I use not 0.1, instead of that, I will use a 1. So 10 log of 1, log 1 is 0. Do you agree?
Yes.
So that means 0 dBg corresponding to
1 mm.
0 dBg corresponding to
1 mm.
1 mm. Agree?
Yes, sir.
And for example, 10 के लिए कितना होगा? Log 10 of 10 is 1.
1.
That means 60 dB.
Yeah.
dBg. So that means for 0.1 mm, it is minus 60 dBg, and 10 mm के लिए exactly opposite.
Yes.
That means 60 dBg plus 60 dBg आ गया for even a single rain droplet. Do you understand? For
Yes.
0.1 it is minus 60 dBg. For 1 it is a 0 dBg.
0.
And for 10 it is
60.
a 60 dBg.
Yeah.
So entire rain droplet का sizes में आपको कितना से कितना तक आ रहा है? minus 60 dBg to 60 dBg variability है, reflectivity scale. Why I have taken them in a log scale is because it is easy. Otherwise, you can have to make a many almost like minus 60 to plus 60. That means 120 scale. That is 10 to the power of 120 numbers you have to create. उसको मैं means small scale में लाने के लिए log apply किया था. Log में क्या होता है? छोटा चीज बड़ा दिख लेता है, बड़ा चीज छोटा दिख लेता है. That is the greatness of the log scale. The range of the radar returns is spread in a very big range. That's why I used the log scale there. ठीक है?
Okay, yeah.
And इसलिए dB को ऐड किया, but last में Z क्यों किया? Because this is a Z parameter करके आपको बताने के लिए dBz किया. ठीक है? But its unit is very confusing because we never uses millimeters and meters in the same scale. But that is what is the universal definition for this radar reflectivity के लिए, because we converted the millimeter size rain droplets or the cloud droplets into a reflectivity. This we have to bear it like this. Z is equal to mm power 6 or meter cube, or otherwise उसको ये सब हटाकर dBz करके लिख सकता है उसका units.
Okay,
Do you
sir.
understand?
Yeah.
So आपको अभी weather radar equation, both point target and weather radar equation and its examples, everything we have learned now. ठीक है? So this is the, for example, if is a insect is there, so use a backscattering cross section to the power of divided by r power 4 for a point target, whereas by r square for the weather targets.
Okay.
Understand?
Yeah.
Now,
Yes, sir.
backscattering cross section. Yes, please.
Go
Somebody want a question?
on.
No, sir.
Okay. Now, I already told in the volume concept, volume reflectivity eta or a reflectivity of a uniform rain को मैंने लेकर sigma I, which is called Z. So Z को मैं different wavelength, different radar frequency में क्या क्या backscattering cross section होता है देख लीजिए. मैंने बताया था S band is little less sensitive than the X band, right? Because smaller is the wavelength, it is more is sensitive to the rain. So if you see, for example, a drizzle of 14 dBg, so you will get a backscattering cross section of minus 120 dBg, very very weak signal. Whereas X band में minus 81 dB आता है. Means आपका X band is very sensitive for the drizzle, and for rain, for example, if you have a radar reflectivity, maybe QPA कैलकुलेट करने वाला कोई होता है तो अभी से आप बहुत सावधान से सुनना चाहिए था. If it is a rainfall rate is 14, that is a drizzle, that means 14. If it is the reflectivity में radar reflectivity is the standard things like a meters everywhere. If you measure the same thing in any radar, so 14 dBg आ गया तो आपको drizzle करके होता है. That means 0.25 mm per hour rain को 14 dBg में दिखता है radar में. And if it is a 1 mm per hour, it will show 23 dBgs scale. And if it is a moderate rain, 4 mm per hour आता है, that is 32 dBg. If it is a heavy rain, say 10 mm के ऊपर होता है तो heavy rain होता है, then your radar will show red reflectivity, that is 41 dBg or and above. Do you understand this classification? But different radar frequencies works differently. X band is more sensitive, that means it is backscattering cross section बहुत strong होता है, whereas compared to S band, X band is much stronger, and C band is moderate. So that is called, that's why C band is also, while it is defined compromise between the S and C band, that's why it is called C band, 5.6 GHz, whereas X band is 9.3 GHz S band. But the backscattering cross section is very good at X band because smaller is the wavelength, its sensitivity will be more. Okay, now I am coming to attenuation, because the same, I told already, the same sensitivity is also going to be a problem for its sensitivity, it is also attenuates. For example, एक छोटा बच्चा होता है, वो बहुत ही sensitive होता है, but is vulnerable for the many diseases. Even he will attack by anything very quickly, right? So that is the problem with X band. It is sensitive, but it also attenuates. For every kilometer, how much dB it attenuates? If you see, for a light rain, 1.25 mm of rainfall, a 25 dBg reflectivity, S band में बिल्कुल attenuation नहीं है, 0.000. C band में भी, are you following me?
Yes, sir.
If it is C band, that is a 5.5 centimeter wavelength radar, there also no problem. But X band also no problem. But if you come to K band, you are 0.4 dB per kilometer में problem आ रहा है. That means K band able to sustain some extent for light rain, but if you see W band, it is already entering almost 1.15. That means W band not at all a candidate for a rain purpose. K band some extent can be used in a light rain, but it is very good. All the 3 SCX में आप use कर सकते हैं. Let us see the heavy rain. When it is a heavy rain, 25 mm per hour rainfall हो रहा है, and reflectivity is 45 dBg हो रहा है, but S band is get in a third decimal point में 0.07 आया था per 1 kilometer. For example, after 100 kilometer, ओके उसको किधर आ जाता है 0.7 पर अप टू 100 किलोमीटर रेनिंग रीजन होता है तो 0.7 mm हो जाता है. So S band also get attenuate if it is a raining for a almost 100 kilometer area में rain हो रहा है तो that is something like a monsoon region. We almost get a more than a 200 kilometer or 300 kilometer continuous rain होता ही रहता है. So at that time it may get little problem. In a heavy rain, S band also requires some attenuation correction. But C band furthermore and X band very high. And if you go to K band, it won't work at all. In heavy rain, it is already 7 dB per kilometer. For example, if you go for a 3-4 kilometers, it is already 21 dB जी चली जाता है. उसको क्या useful होगा? So that's why K band radar and W band radar cannot be used above the light rains. Whereas you can use X band maybe up to heavy rain में heavy rain के ऊपर से. That means heavy rain and extreme rains में X band का usefulness कुछ भी नहीं होगा because it is attenuating per kilometer 1 dB उसका सत्यानाश हो रहा है उसके इसीलिए X band भी not a good candidate but उसको correction कर पाए तो that means by using a polarimetry maybe X band can be used to some extent but not in the extreme rainfall event especially maybe up to heavy rain or heavy rain तक use कर सकता है. But C band को use कर सकता है extreme rainfall event में if it is having some polarimetric capability because using polarimetric capability जो attenuate हो रहा है इसको हम recover कर सकता है उसको हम correction कर सकता है. So attenuation भी थोड़ा extent तक ही correct कर सकता है because वो पूरा probing ही नहीं हो पा रहा है तो like in X band or K band तो further probing ही चली जाता है. That means forward scattering completely बंद हो जाता है. That means the red signal मैंने radar पिक्चर में दिखाया ना एक इमेज दिखाया ना कार्टून उसमें रेड सिग्नल दिख रहा है वो रेड सिग्नल ही बंद हो जाता है बिकॉज हेवी रेन में क्या होता है वो रेड सिग्नल कंप्लीटली एब्जॉर्ब बाय द रेन पार्टिकल्स सो दैट्स व्हाई सिग्नल फॉरवर्ड नहीं चली जाता फॉरवर्ड नहीं जाता है तो फॉरवर्ड प्रोबिंग बंद हो जाता है. फॉर एग्जांपल 20 किलोमीटर के पास फॉरवर्ड प्रोबिंग बंद होता है तो इवन इट इज 100 किलोमीटर आपने रडार इक्वेशन यूज कर उसको 100 किलोमीटर प्रोबिंग बता रहा था बट वो 25 किलोमीटर के पास ही बंद पड़ा है सो आपने रिमेनिंग 75 किलोमीटर नहीं देख पाएगा. इसीलिए के बैंड एंड डब्ल्यू बैंड बिल्कुल रेन के लिए यूज नहीं करना है हेवी रेन के लिए एंड एक्स बैंड थोड़ा यूज कर सकता है इफ इट इज अ पोलरिमेट्रिक रडार करेक्शन कर सी बैंड को कॉम्प्रोमाइज यूज कर सकता है एंड एस बैंड इज बिल्कुल वेरी गुड. For example, S band extreme rainfall में 1.5 that means up to 100 kilometers S band को ऐसी use कर सकता है because it is only 0.15 kilometer per at 100 kilometer के region of rain में so उसको actually S band is a very robust in any type of rain it can be used especially from moderate rain to extreme rainfall events में S band में use कर. Let us see the Hamid interest is he want to study the snow. Okay, snow के अंदर में देख रहा है तो attenuation बिल्कुल नहीं है. S C X are very much okay. But in a K band or a W band, significantly affecting little bit for each kilometer. That may be also a boon for these radars because this can be used for the attenuation instead of ZR relation. Attenuation and snowfall can be estimated. So this could be this last three things can be used in that way. In the fog के लिए भी use कर सकता है. Fog में means S band is little attenuating in a heavy fog में, so उसको भी ये use कर सकता है. This is the chart. I will end here. So this is the first part of the my things. Is there any doubt?
No, sir.
Is it clear?
Yeah, it's clear.
Yeah, fundamentals of the radar equation मैंने नहीं बताया था, but fundamentals of weather radars. If I would like to ask Kishore sir.
Yeah, tell me sir.
What I want to say is now it is already initial first 30 minutes hiccups and switching over to there to here. So what I want to say is maybe today we'll off, maybe If it is at tomorrow, so very quickly within a 40 minutes, I want to close with the same Google thing, Google meeting. Google Meet. Will quickly in a 40 minutes I will cover the fundamentals of the weather radar, where actually I want to cut the beam into small pulses. I will say the beam concept, pulse width concept, and each elevation and azimuth कैसा radar को rotate करता है तो कौन सा display आता है. That means plane position indication क्या है, RHA क्या है, vertical looking क्या है, ये सब बताकर what is the usefulness of surveillance radar मैं आपको एक pictorially and some data लेकर आपको explain करना चाहता हूँ. बट आज का क्लास बहुत महत्वपूर्ण है. आप रडार इक्वेशन दोनों सीख लिया. दैट मीन्स एक बड़ा क्वेश्चन है आपको आ जाता है. व्हाट इज रडार इक्वेशन, व्हाट इज इट्स लिमिटेशंस, व्हाट इज इट्स बेनिफिट, एंड explain the radar equation with a block diagram, the either point radar equation or the distributed target radar equation. Otherwise I can ask what is the difference between the point target radar equation and distributed target radar equation. So the today class will cover most of the questions for your examination point of view, either in an exam, in your university exam, or in interviews also. This will be very useful class. Are you getting?
Yeah.
So today shall we start to digest this class?
Yeah, 1 minute, sir. Students, do you have any class tomorrow? Other classes?
Sir, we have exam.
Which exam?
That human
Human right education.
human rights. Yeah,
What time?
need to study.
Human rights exam is okay. I don't want to
I
tell
would like
anything.
to say one thing. Can I
Yeah.
say?
So, yeah, tell me.
Yeah. Yeah, I'm sorry because when I'm involved with the class, I will go and I will take extra time to explain, because I want to reach the student with very, very basic fundamentals. That's why I took a time. I'm sorry I couldn't able to cover in 2 class, but I required one more class where I can cover the fundamentals. Definitely it is very exciting. Actual radars working you can imagine there. So that's why I would like to have one more class to cover the very fundamental.
That's actually.
We will either tomorrow morning or tomorrow afternoon. So, what time is your exam? Amit.
11.
11.
Huh?
Morning 11.
11.
Okay, then we can, sir, are you available tomorrow at 3 o'clock?
No issue. After 3:30 I can take.
Yeah, okay. 3:30 to 4:30.
Yeah.
Okay, sir.
I will come with only fundamentals of weather radar, because I am covering many yesterday doubts like scattering and reflection and things they asked. I covered little bit that, but in fact I brushed them.
Okay.
But you people please go through either internet or something or basic textbooks. You will get all these fundamentals which are very required, but because our constraint of classes, I quickly covered. But main thing is radar equation. I don't want to pick there because it's a very basic. If you understand these fundamentals, you can hit any radar, whether it is a military radar or a snow study. So anything you can do. So this is a fundamental part. So hope if you have any doubt, even a minute doubt, please clear and go from this class.
Okay, sir. Let me fix first this one. Okay, students, 3:30 to 4:30 tomorrow.
Sure, sir.
Okay, is it okay for everyone? Or,
Sir, it's not possible to take afternoon today.
today afternoon?
Today I have actually I skipped and I told my wife that only 1 hour I am going. I will come and help you.
See,
Because-
it's a holiday, so because we requested him, so he taking today.
No. For me it's not a holiday, but घर में पूजा हो रहा था, उसके साथ रहकर help करना था, because we both are in fasting, so she required some help.
It's okay, sir. We can
Okay,
attend
no
tomorrow.
worries.
Okay.
Tomorrow,
Okay, if it is a problem tomorrow, day after tomorrow also I can take.
Actually,
Okay.
day after tomorrow we have internal exam.
So fix it tomorrow. We're going to fix it tomorrow, 3:30 to 4:30, and then
Let us know, Neelam, what is the problem from tomorrow afternoon? Do you want to go somewhere?
No, actually, I don't have any problem, but I want to study. At the day after tomorrow, we have an internal exam.
Okay, after 2 days के बाद ले सकता है.
No,
Is
no,
it
no, no,
doable?
no, sir. So
Okay,
we can't
okay.
go beyond tomorrow.
Okay.
We're going to
Yeah,
take.
okay, I'm okay.
They have,
Okay,
they have
otherwise I
study.
can tell you one thing. Today night we can take like after 7 o'clock or 8 o'clock. क्योंकि मेरा पूजा तो 7:30 को हो जाएगा. पूजा में पेट का भी पूजा हो जाएगा, उपास होगा ना. Is it okay night or you have to prepare for tomorrow class today night?
Sir, it is okay. I think it is fine. Tomorrow 3:30 to 4:30. We please take the class.
Okay, I will quickly finish there.
Okay, sir. Good.
Is it okay, all of you?
Yes, sir.
Okay, thank you. I won't take much time, but I request you to go through the material what Kishore sir shared, so and understand that one. And fundamentals का इसमें नहीं है. Dr. Kishore, I have given one more PDF, I think, that is for fundamentals of weather radars. You might not have shared.
I will check it and then I will. If it is
Yeah,
available,
please share and send a mail to me and Meenu also.
Okay, sure.
Okay, the same material you can use for preparation so that I will come tomorrow little faster. I can go.
Sure, sir.
So now I would like to ask Mayur, Shailendra, and Minu, and one more, I think. So, do you does this equations made you any problem, or is it gone into your heart?
No, sir, it's okay, sir.
It's
Do you understand what is it? What is the weather radar? Why weather radar target is called distributed target? Can anybody answer other than Syed and Neelam? Hello? Anyone? Minu trying to help. Minu, you want to say something?
We are not focusing on a single target. No, the weather systems are distributions, so that is why we are using distributed targets.
Can you use the concept of macroscopic particles and microscopic particles? For example, a cloud, when you see with the naked eye, it is a very big size. So it's a macroscopic.
But the particles are microscopic particles.
Means it is smaller size, like they are in millimeter size. Okay. So they will be million in numbers. So main thing is here small particles का reflect backscattering cross section is integrate होता है in a particular volume में. Radar equation ही use करो. Radar equation में हमने क्या invoke किया? Volume का invoke किया. Volume is nothing but finite beam width and finite pulse width. Because within the finite beam width and within a finite pulse width, how many particles are there? Those each particle का backscattering cross section integrate करता है तो उसका diameters लेता है तो then radar reflectivity Z आता है, right? Whereas if it is a point target, what you will get, even with a single pulse, you will get a lot of return back. That is a reflection. So that particular signal, if you analyze to the power of r power 4, the transmitted frequency divided by r power 4 किया तो आपका उसका रेंज पता चल जाता है, right? So that means airplane आपको some 3-5 kilometers दूर से आ रहा है तो उसका साइज के हिसाब से it intercepts a lot of energy back because of physical size of the target is very big. It intercepts more energy so that at receiving point you have a lot of strong energy, and so the strong energy will be in the receiver. It will be analyzed and will be calculated its characteristics. So on the equation, point target equation. Yeah. Now I want to know from Mayur or Shailendra or maybe who else, or maybe Neelam. So can you tell me why the simple radar equation is not a complete radar equation? Maybe Hamid also can talk.
Yeah, sir.
Yeah.
Because it's having some disadvantage. Simple radar equation having lots of disadvantage, just like fluctuation in a target shape and the size in a target. Means we consider the spherical shift, but the
Good,
shapes
Neelam.
are different also.
Excellent point. That means what Neelam want to say is that because size and shape of the target will be in a different look angle, it will look like it differently. For example, if you see when an aeroplane in one direction, its horizontal length is very big, but when you see perpendicular to that particular direction, its nose part is very small. So that all things comes into picture. That fluctuations we are not taken into consideration in the radar equation. That is one point she is telling. Can anybody help the other 2 points? I will ask you directly. Mayur? Yeah,
Hello.
Shailendra, please tell me.
Electronic noise is not considered in simple.
Excellent. So what he want to say is in a radar, transmitter is there, receiver is there, and antennas. These all will be connected by different wires, or the waveguides, or maybe connections. So because of this one, there will be some losses will be there. That means conducting losses are the all these things is the electronic noise, and because of that some noise losses will be there. These losses are not kept in that radar equation. That's why it is a simple radar equation. So that's why it is not complete. So now I will ask the Mayur to add one more. Can you guess what Neelam and Shailendra not complimented? You can compliment that point. Mayur, can you speak? Is your thing is audio is mute. You can unmute and talk. Rishikesh also I could see, and another one is way to Mr. 360 somebody. Who is that?
Prashant.
Okay, Prashant, you can tell me. Prashant, Rishikesh and Mayur can speak out to add why it is called simple radar equation, what is its limitation. In that 2 points already Neelam and Shailendra shared. You can share. They have a muting problem or what?
No.
Can you ask them to speak? Anyone?
I think. Hello.
One loss is due to the radar electronics path losses, and another one is the statistical fluctuation of the target. This is explained. What is the other 2 factors? Because in class I explained the limitation. Yes, Mayur, tell me.
Sir, motion of the cloud or the moving object may be.
Motion की वजह से क्या हो सकता है? Doppler, by its phase we can know its motion by the Doppler. But उसका limitation क्यों नहीं है? Means radar equation में, simple radar equation में मैंने velocity को नहीं लाया करके बोल रहा था, और what you want? एक तो मैं क्लास में नहीं बताया, उसके बारे में मैं आपके साथ सुनता हूँ हम सब, बट क्लास में जो बताया था, so there are the 4 points I told. So 2 things is covered. One is due to the electronics part noisy, the path of the electronics and its noise things is one real fluctuation, because it's a very random fluctuation that should be taken care. So that is Shailendra helped. So Neelima helped for the what she helped? Maybe
Target shape.
Size and shape is. And what else? We have not really taken in radar equation.
Volume. We don't consider volume in simple radar equation. Do we?
Okay. So this is not exclusively came, yeah, because in the radar equation we have neither used the volume concept, because volume concept is required for the distributed target, where the shape of the pulse width and shape of the beam width and uska correction factor भी मैंने 1/2 log 2 एक introduce किया, that is for beam filling factor, and another one is the shape of the beams, that is 5/4 something we used. Similar way some corrections are required, so that is correct. So that may be helped by Mayur, right? Who else?
And effective aperture.
Rishikesh? Syed, yes, please.
And effective aperture.
Effective aperture is already there in the radar equation. You no need to bother about it, right?
Sir, I don't get it correctly. What does it mean, effective aperture, actually?
Effective aperture is the how electrically it is effective to collimate the either sending time to collimate towards the atmosphere while is receiving time. So it is something like this. For example, I can cut this one. So if I make a cone, oh no, not it. This is not a cone at all. Oh no. So I can rotate this? No. Maybe better is that I can go with my word.
Solid angle.
Yeah. Microsoft Word. Yeah, Microsoft Word is there. Oh. For example, a physical antenna size is something like 10-meter antenna, but electrically it is only some part of it is exactly pointing out in the atmosphere से जो energy आया था ना, वो focal point में चली जाना चाहिए. That means there is a small collimating lens I kept. There all these parallel beams has to be collimated. तो उसके लिए मैं एक insert, okay. So maybe picture shapes. I can go into the shapes. Oh, बहुत time ले रहा है. Could you able to see my screen?
Yes, sir.
Yes, sir.
No, sir.
बीच में आप दो लोग ऋषिकेश and another guy can think that what you can contribute, what other two things you can tell.
I think there is solid angle, sir. We can also Google it, right?
Pardon?
We can Google it directly.
Yeah. But I just want to show, for example, this is the curvature, and the beam center point is here. All right. I can just rotate like this. Okay. So the when call estimating, yeah, how can I show that? Okay, that is maybe better. We will Google it.
So you can go in images.
Yeah, yeah, I got it. So here you see, here you see this is a parabolic dish, and when the feed is dispersing its energy in all direction on this plate, so this energy initially goes like this, and a parallel wavefront will come. That means these are the parallel beams. So from radar, say when it is transmitting, the feed will throw all the beams onto this reflector, and they will get parallel to the transmission. So these parallel beams will go into the atmosphere. Okay, the opposite is also true. When the return energy comes, these all parallel beams will come back, and this all will be collimated towards the feed. If this has to happen, that means this reflector should be a highly polished. Okay.
Okay, sir.
So highly polished होता है तो वो होगा, नहीं तो if it is a rugged thing, so all pulses may not reach to the feed. So that is called the efficiency of the electrical efficiency or electronic efficiency of that antenna. If it is highly efficient antenna, that means highly polished antenna, all the rays which is touching this parallel beams touching, all will be collimated and very high intense signal will be feeded to the receiver section. Otherwise, very less amount of energy will come. Is it clear? So this part is already came in the radar equation. But what it is not came is, maybe we can listen to way to Mr. 360 or Rishikesh. That means antenna physics is very much important factor for the quality of the radar. So this is came as AE करके मैं लेकर आया था, इसलिए एंटीना का point is already taken care. What points is not taken care is really a noise things due to the electronics, and another thing is the shape and size of the target, and another thing in the radar equation I have used 5 things which is nobody is telling. One is transmitter, receiver,
Modulator.
antenna, and target. What is the 5th one?
Modulator.
Environmental.
Sorry, environment.
एनवायरमेंट का यूज कर आप तो बहुत बात कर सकता है.
Yes, yes, yes.
कोई ने बताया था सर क्लाउड का मूवमेंट है ये सब, इसीलिए उसको मान लिया था मैं मयूर को. बट ऋषिकेश एंड थिंग्स एटमॉस्फेयर से जो अटेन्यूएशन होता है वो बात आपने नहीं बताया था. मैंने अटेन्यूएशन बताया था, बैक स्कैटरिंग क्रॉस सेक्शन बताया था, माई स्कैटरिंग बोला और रैली स्कैटरिंग बोला है. ये सबको इक्वेशन में नहीं लेकर आया था. And for example, if it is a smallest particles like aerosols, it cannot observe because its backscattering cross section is very small. वो part कोई नहीं लाया. And environmental के attenuation part is not there. So attenuation बताता है तो atmospheric environmental attenuation because of the snow or hail or rain part, attenuation बहुत ही important thing. This is a biggest thing you have to contribute. So Rishikesh, what is the problem? Yeah, could you understand now?
Yes, sir.
Who is that? Praveen? Who is that? Way to 360?
Prashant, sir.
Yeah, Prashant, could you understand? So what is now?
Yes,
You
sir,
can
I have
conclude
got-
me.
I will
What
have
are the...
ask something. Hello.
Please.
Hello. Sir, you said
Yes, sir, please.
some attenuation, but I have doubts on in single radar we have only targeting one, consider one target. But how about the diabetic heating is present on atmosphere?
डायबिटिक हीटिंग को आपने क्यों लाना चाहता है रडार इक्वेशन में? पहला वो बताइए.
Sir, you
रडार
said
को टेम्परेचर रडार का सिग्नल
So,
टेम्परेचर डिपेंडेंट करके मैं कुछ बताया क्या रडार इक्वेशन में?
no, sir, but you said variability in three ways, na?
No, variability in the target size or maybe the variability of the signal statistics in the that is called noisy, either due to electronics because of the temperature. Electronics को temperature dependent होता है उसका thermal noise ज़्यादा होने के लिए. For example, if radar is operating in a 40 degree centigrade, your temperature के हिसाब से electronics का अंदर जो atoms होता है वो वाइब्रेट होना शुरू हो जाता है, उसकी वजह से नॉइस आता है. फॉर एग्जांपल, इफ ऑल रडार इलेक्ट्रॉनिक्स वर्किंग अंडर minus 20 degree centigrade, you won't have a much noise. That is called thermal noise. वो रडार का नॉइस कम करना है तो कुछ क्रायोजेनिक्स के इंजन में डालकर ऑपरेट कर सकता है. So that is what the satellites, when we are sending, we are keeping a lot of noise बंद करने के लिए उसको cosmic shield लगा देता है. वो सब it's a different electronics, a different noisy things, but thermal something आपने जो बोल रहा है, so why you are deviating from the center point? Because if you want to create a complexity, so you can, because what I want to say is a smart person can simplify the complex things. Okay, at the same time the opposite thing, one can complicate these simple things into a very clumsy, then we will enter into a very noisy thing, I mean clumsy atmosphere. So here in the radar things, I never told anything about the temperature point. Of course it will be there, but I have not told. The main thing is it is the characteristics of the temperature transmitter, characteristics of the receiver, characteristics of the antenna, and the characteristics of the target, and finally the environment. Only these 5 factors will dictate करके radar equation ने लेकर आया था, ये मैं नहीं बताया था. So जो पहला radar maybe some 100 years back when the war time baby it is, so that time these are the general rules and regulations they made to understand the radar, where they never made anything. This is enough for the radar to be characterized. Why you want to bring the temperature? So you can bring it, but that is an advanced thing. But I want to make a simplify because a common person in the class who is sitting, he should also understand your point. We will discuss off the class, maybe across the bench, across the tea time, we can share anything. But here all people who are listening, they want to really understand the basic concepts. So in that aspect, you can ask any question. Or otherwise you contribute to the point what we are discussing.
Sir,
Yes, please.
does turbulence have a role in radars?
Excellent. So that is called the atmospheric statistics. That means when there is a atmosphere is very clumsy, that means it is a lot of winds, shears and all these things, then turbulence will create. So, but in the radar equation, which I have not explained, in the radar things, the target, when the target returns comes, amplitude and phase information I am using. So from that one spectrum I can make. In that spectra, the signal, that means amplitude of the radar signal is called the area under the radar signal is called the reflectivity. That is called signal to noise ratio, which is used to calculate the radar reflectivity Z. Okay, the other movement from the radar spectrum we will calculate is the how much this signal is shifted from the central frequency of the radar. It is called the Doppler. So that is called the rate of change of phase. By means of it, what is the target motion I can calculate. And the other second movement is called the, or otherwise 0th movement is the Z, first movement is the Doppler, and second moment is called the spectral width, which can measure the statistical fluctuations associated with the target, associated with the distributed targets, because all rain droplets in a volume may not move in the same direction. If all move same direction, I will get a spike, or otherwise if they are moving randomly, I will get a Gaussian shape signal. That means if my signal is Gaussian, that means it is a bell shaped, then that means the particles are very much randomly moving. It indicates the very much randomly moving. This part is not there in the radar equation. Yes, I agree.
Okay, sir.
Who is that? Rashikesh.
Yes.
Great. So it is not that Prashant is wrong, but Prashant thinks is a so minute thing which cannot be included anywhere, which cannot be explained in this class. So which is a very minute aspect. It is indirectly affects the temperature of the target, but is very weakly known, because macroscopic property of a target only we can know, and its microscopic things, especially it came into the radar equation, dielectric constant. That means if it is a hot target, its dielectric constant nowhere into the picture, because I have not mentioned. But in a radar equation, I have in radar weather radar equation, I have shown the dielectric constant. There it will give temperature can come into picture. Okay, but in an aeroplane, whether it is a firing aeroplane is burning, or otherwise anything, I don't know, because I have not we worked on that. But definitely we can go through book and we can explain that the temperature, body temperature of a aeroplane thing, how much it helps to get a reflection things. It is a very weakly, because it's how much it is reflecting, whether it is a cold surface or hard surface or same yoga almost. It may change very little bit. Is it clear, Prashant?
Yes, sir.
Yeah. Now you can add me if anything relevant to the weather radar equation or the A equation में जो नहीं है radar equation, simple radar equation में, उसको लाने के लिए कोशिश कर सकता
Sir,
है.
I have a question.
Yes,
If the size of the target is less than
Yeah.
the wavelength,
Yeah.
then it falls into which region?
Rally scattering.
Okay. Okay. Yeah.
Okay. One thing, because of this class, or even today in the radar meteorologist or anywhere, any radar people couldn't be able to control. One thing is that simple radar equation, one radar equation, they just in the background signal processing में डालकर रखता है. But you people could have asked that, sir, it is raining, highly raining, liquid water fall हो रहा था. Suddenly, if the rain becomes snow, okay, whether the radar equation is taken care. Mathematically, it is taken care. 0.9 and 0.2 I told dielectric constant में डालना है, but it is a signal processing wise difficulty that it cannot adaptively can change the radar equation if it is a snow करके, because this is a radar, it is not a robot or it is not a human brain. Because by seeing, we can know that now it is changing from the liquid to the ice phase. उसके लिए आपको radar equation में 0.2 डाल सकता है, but mission में 0.2 वो नहीं डाल सकता है, because computer में वो अपने आप समझ में नहीं पाता है. इसी की वजह से bright band at the melting region, that means at 0 degrees centigrade, bright band होता है, उसको the reflectivity increases by 7 dBg is an artifact of the radar. Why बोला हुआ है? Because my radar equation is kept delta k square 0.9, but now I have to change it to 0.2. That's why it is the amplification. Yes, please. कोई बोल रहा है? Yes, please.
Yeah,
Any question?
Prashant, but
Question?
no one is talking, sir.
Okay. So is it clear today's class?
Yes, sir.
If you are not asking question, I will be asking many questions at the end.
Sir,
It
why
may be-
do we introduce backscattering cross-sectional area? Is there any
Because, for example, the same radar equation is encounter both Rayleigh scatter particles and my scattering particles. You should know what wavelength I am using, and according to this wavelength, what is the Rayleigh scattering particle regions, what is the my scattering particle region. Then you can able to guess or predict that. So this is the correct part up to this low rain part. K-band radar is working good, but once it is entering into a my scattering, you know that radar equation को correction चाहिए, or sometimes you can know that radar equation correct करने के बाद भी कुछ गलती बताएगा, क्योंकि it is already deep into the my scattering.
But what we calculate here, we assume targets are spherical. What about which aren't spherical? Are we considering birds are also spherical?
Can you repeat the question?
Are we considering birds and insects also spherical? Because we are
That's
considering mainly spherical.
That's what I'm telling. If you have the radar equation which I discussed, if you have a complete hold of it, okay, and if you know your real atmosphere and about environment, okay, environment में क्या होता है? For example, what Hamid is helping you by his question is that this is a very genuine question and very, for example, in the atmosphere, whatever the liquid water bodies existing, those are all, when I am putting my weather radar, a beam in a particular direction, in the particular finite beam width and finite volume, there are the liquid bodies. That may be snow, or maybe ice, or maybe a water vapor, or maybe a rain droplets. Okay, besides to these meteorological targets, if some non-meteorological water body came, for example, if it is a insect को radar कैसा देखता है? इसको body के अंदर कुछ पानी होता है, वो पानी को देखता है. For example, if it is a bird, वो bird के अंदर पानी होता है, उसको भी वो पानी जैसी देखता है.
Okay.
Any body, for example, any body को वो water body की तरह देखता है, but water नहीं होता है तो, for example, if it is a dry body, it cannot able to see that because of water body. But it is your knowledge that if that water body in the finite radar beam volume beam में वो water body is due to the real meteorological water body or a non-meteorological water body. Non-meteorological water body means either insect ho, bird ho. This also this radar will see as a liquid droplet only. But उसको different shape होगा, size होगा, but इसका अंदर पानी की वजह से वो देख रहा है. For this, what I want to say is, for example, your micro oven, उसमें क्या है? आपने एक शीशा, that means ये glass के अंदर microwave safe glass में पानी डाला है और समोसा डाला है, ये दोनों को गर्म कर देता है. और अदरवाइज केशनट डाला है, उसको भी गर्म कर देता है. For example, if you keep some non-metal water जो नहीं होता है, for example, एक आयरन का पीस, एक आयरन का नट डाला है, वो हीट नहीं होता है, because उसका अंदर डाइलेक्ट्रिक कांस्टेंट, because वाटर बॉडी इज अ डाइलेक्ट्रिक बॉडी, उसको डाइपोल को हीट कर देता है.
Okay.
वो डाइपोल की हीटिंग की वजह से, वो इंटरनल हीटिंग की वजह से वो हीट होता है. So similar things, microwaves, when it is transmitting in the atmosphere, that microwave energy will heats up, or otherwise it वो those dielectric bodies वो ऐसा होता है तो उसको resonate होकर back scattering होता है, उसकी वजह से water bodies होना चाहिए था. Is it clear now? So now the question further, the answer extend to this question. For example, if it is a bird आया था, okay, bird का liquid किधर efficiently organize होता है, उसका body के middle portion में होता है, वो little spherical size हो गया है तो, but ये bird क्या है, it is not going background advection से चली जाता नहीं है. For example, background बाहर advection हो रहा है तो clouds उसकी हिसाब से move होना चाहता है. For example, monsoon winds are moving in the lower atmosphere westerly, so your water vapor or clouds will move westerly from the Arabian Sea towards the Bay of Bengal, right? The motion is passive. That means it cannot dictate its motion, whereas insects or the birds have their own, at their will, they can change their direction. That means when the winds are moving opposite to it, it can just go, it resist and it flow with a high energy apply कर उसको resistance force डालकर आगे चली जाता है. So that is the property of insects. Living beings property क्या होता है उसका, at their will they can change this. So this का statistical fluctuation of the radar signal को use कर ये दोनों को हम separate कर सकता है. This is what one publication we made. इंसेक्ट्स एंड बर्ड्स को आइडेंटिफाई कर उसको निकाल दिया था, क्या बताकर, उसको नॉन मेट्रोलॉजिकल टारगेट बताकर उसको निकाल दिया था.
ओके.
सो उसका पर्टिकुलर प्रॉपर्टी होता है, रडार में देखते देखते आपको पता चलता है.
बट माय क्वेश्चन वाज अबाउट इट्स शेप. वी हियर कंसीडर ओनली स्फेरिकल.
वही बोल रहा था, वो शेप है अकॉर्डिंग टू इट्स लिक्विड डिस्ट्रीब्यूशन इन इट्स बॉडी.
ओके ओके.
उसका शेप अलग होता है. आपने जो देखने वाला का बर्ड का शेप एक जैसा होता है, बट इसका अंदर का वाटर का बॉडी इफेक्टिवली कैसा डिस्ट्रीब्यूट हुआ उसकी तरह होता है. फॉर एग्जांपल इफ इट इज ए स्मॉल, फॉर एग्जांपल इफ इट इज ए पिजियन, यू मे सी इट इज लाइक ऑलमोस्ट लाइक ए स्टिक. फॉर एग्जांपल इफ इट इज ए पेलिकन, यू कैन सी लाइक ए सम हॉरिजॉन्टल लाइन.
यस.
So it depends upon how effectively its water is distributed inside the body. What I mean is it's a liquid. उसका अंदर खून होता है, वो उसका अंदर भी थोड़ा water की वजह से बनता है. For example, our body is made up of more than 85% of the is water.
Yes.
Right? So but वो water कैसा distribute होता है? Maximum water में भी पेड़ में होता है, हमको थोड़ा अलग जगह में भी distribute होता है. इसीलिए our infrared radiation capability of body is, for example, armpit में and some very located place where the humidity ज़्यादा होता है. For example, armpit में आपको sweating होता है and genital places में भी ज़्यादा sweating होता है. So those places will illuminate lot. When I am seeing any human being in a infrared goggle, I can see where the humidity is more in the where the radiation humidity more is. That means infrared energy radiation किधर ज़्यादा होता है, आपको sweating का जगह में ज़्यादा होता है.
Okay.
So that means those are the hot spots of your body for your water location. Similar way for birds के लिए अलग होगा. Are you getting?
Yes, sir.
Great. So because the cloud becomes the rain, so for example, as long as my cloud radar is operating in a cloud, non-precipitating cloud region, it is well in the Rayleigh scattering region. But suddenly when it is becoming rain, so it is entering into a heavy rain, so it is changing the Rayleigh scattering into my scattering. So इसके लिए मैं Rayleigh scattering and my scattering क्यों बताया था आपको, ये knowledge उस समय क्लिक करना है. Now ये cloud तो rain की तरह change हो रहा है, तो that means scattering change हो रहा है, that means correction apply करना पड़ेगा. So but in the radar background equation में जो डाला था, I am sorry that my battery is going to exhaust. It can cut any time, but I want to explain continuously. So when same radar, same wavelength is using for both cloud and rain, it sometimes it enters from the Rayleigh scattering to my scattering. That correction also has to be applied by the research scientist. So वो तो radar equation में नहीं ला सकता है, मैथमेटिकली में लेकर आया था, बट उसको इन्वोक करना पड़ेगा. बिकॉज एक ही इक्वेशन में डालता हूँ सिग्नल प्रोसेसिंग का टाइम में, उसको चेंज करना पड़ेगा बाद में.
ओके.
बिकॉज सेम रडार आई एम यूजिंग फॉर दी एट सरफेस एट 0 डिग्री आइसोथर्म आल्सो, इसलिए फेस चेंज हो रहा है, फेस चेंज भी आपने अप्लाई करना पड़ेगा बाद में. सो दैट इज द कॉम्प्लेक्सिटी. Because I told that earth curvature also comes into picture. This is one of the limitation of the radar, simple radar equation. So this is not came. So these are the many points a simple radar equation की हिसाब से weather radar की तरह आपने, मैंने ज़्यादा explain किया आज. कल next when I am invoking, it is a short class. Quickly I will recap all those things there. Okay. Yes, next sir. Class is very important class. Don't miss it.
Sure, sir. Thank you.
Is my class is how you rate it?
10 on 10.
Oh, perfect. Thank you. That means आपने कुछ grasp किया.
Hello, sir.
Okay.
So thanks for
Great.
starting from basic. That's it.
Yeah, because what I want to make is last year one student of your senior, what he told is he has given a GATE exam. This was highly helped him to write his own because he listened the class. He just wrote the descriptive question there.
But
That's
he
what
didn't qualify.
not only one student, 2-3 students told me that in the GATE exam after they passing they came with a suite. सर आपका क्लास की वजह से मैं बहुत सारा फिजिक्स को अच्छी तरह से समझ पाया, मेरा गेट का एग्जाम में अच्छी तरह से एक्सप्लेन कर पाया था. GATE or a UGC net or something. And some people also told in the interviews for the radar question they explained because they are efficiently capture this 2 hours class into their आपका gray matter में, because in the earth in your brain there is 3 different matters. If you put this today's class in your gray matter till your death it will be with you. So that means बहुत ज्ञानी लोग होता है उसको बहुत कॉन्टेम्पलेट कर कर उसका नॉलेज उसका ग्रे मैटर में डालता है. सो आज का क्लास आप एक संदा एक मींस एक बात सुनने के बाद
how to store in the gray matter, please.
Contemplate this is उसको बताता है साधना करना है. फॉर एग्जांपल मींस हिंदू माइथोलॉजी, आई एम नॉट वेरी मच बायस्ड टू हिंदू माइथोलॉजी. इन एनीवेयर they chant. For example, वेदों को चैंटिंग की वजह से अभी तक हमारा पास तक क्यों आया? उस तरफ पुस्तक नहीं है, उस तरफ कुछ भी नहीं है लिखने के लिए. Only thing is they contemplate many times, they kept in their brain and they are given to the next generation. Even in all over the globe, they may not be the Hindus, they may not be the Mohammedans, but there is a हमारे ह्यूमन तरीका में नॉलेज कैसा कंटेम्पलेट किया, उसका जीवन का तत्व में वो जो सहन किया था, उसको साधन किया था, उसको नेक्स्ट लेवल को जनरेशन के लिए सीख लिया था. वो लेवल उसको चांट कर दैट मीन्स बहुत बार उसके ऊपर आप सोच लगाना है. इफ आजकल आप क्या करता है, डायरी में लिख कर रख सकता है, बट एर्लियर पीपल क्या कर सकता है, उसका माइंड में रख कर बार बार कभी कभी उसको मीन्स यू नो काउ फर्स्ट इट ईट्स द ग्रास वेरी क्विकली and later when it's a leisure time it bring it back and it again eat that one.
Yes.
Yeah, that is what we have to do when the knowledge is helping. So you have to take all the knowledge at a time and बार बार उसको क्या करना है, अंदर से बाहर लाकर उसको पॉलिश कर रखना चाहिए था. So उसको क्या बोलता है, contemplation बोलता है, साधना बोलता है. For example, I don't know that cow once it eats and again it will bring it back. In Telugu it is called nemarvestadi. I don't know in Marathi or Hindi उसको क्या बोलते हैं. हाँ
Madhu sir, it's already 1:30. They are hungry.
Let them tell.
You are in fasting also.
Let them tell. If they are hungry, I can leave them.
No, they are not going to tell us. I noticed that.
No, I am given a full freedom. You can exit any time. When I told that my class is closed, you can go any time. But the people are asking the question because they want to how to means imbibe the knowledge into my gray matter. He is asking. So for that, I am explaining. Whomsoever is interested, they can listen. Otherwise, can go to for your food. Okay, Mayur, what I want to say is that if you want to keep in your brain, you have to contemplate. If there are many existing things, you can write, you can derive the equation or you can imagine. Image की तरह रखकर आपके brain में डाल सकता है. Because most of the people's name we remember by their image. उसको इमेज देख कोई बोलता है अरे मैं उसका नजरअंदाज है बट उसका याद नहीं आ रहा है, बट उसका फेस याद आ गया तो वो टक उसका नाम बोल देता है, ये रमेश बपलीहरी कुछ तो बोल देता है. Because sometimes our brain works, it is actually that's why it is called now the brain knowledge is used for the mission language or otherwise artificial intelligence. क्यों कर रहा है, ब्रेन का तरीका नॉलेज रखने का तरीका अलग अलग डायरेक्शंस में होता है. 100 तरीका से वो उसको इम्बाइब करता है, एक इमेज की तरह, एक नाम की तरह, एक साउंड की तरह एंड एक कॉन्टेम्पलेशन की तरह. यू कैन यूज विच एवर इज कन्वीनियंट फॉर यू. यू कैन यूज योर ब्रेन का कैरेक्टरिस्टिक आपको पकड़कर, इसकी साउंड की वजह से होता है तो इसको रिकॉर्ड कर सुन लो. इसके इमेज की वजह से वीडियो बनकर सुन लो. इफ इट इज राइटिंग की वजह से मुझको याद रहता है तो आप पुस्तक में लिख कर रखो. एक्चुअली हमारे बचपन में रीडिंग एंड राइटिंग ही बताता है, बट देर इज ए इमेजिनेशन टेक्निक ऑल्सो. दीज आर ऑल द टेक्निक्स यू हैव टू इन्वोक. दिस इज व्हाट एर्लियर वेदों का समय में क्या करता है, लोग 100 तरीका का शक्ति मालूम होता है कैसा उसको कॉन्टेम्पलेट करना. हमको 3-4 वैरायटी मालूम है अभी, बहुत सारा वैरायटी है इसमें. इसके लिए अलग क्लास ले सकता हूँ, बट अभी ये क्लास में नहीं है. बट इतना आपको काफी है, इशारा काफी है समझदार के लिए. आपको इशारा मिल गया अभी.
यस सर.
Yes, sir. Thank you.
थैंक यू सर.
Yeah, but it is what is your duty is you always prefer how to remember this knowledge. If you always think that how to remember this knowledge question if you आपके साथ होता है तो वो नॉलेज को कैसा रखना आपका बॉडी व्यवस्था कर देता है. बिकॉज दिस इज द प्रेयर. भगवान को अपने क्या प्रेयर कर रहा है, मैं इसको याद करना चाहता हूँ. आपने बचपन से आपका नाम सुन सुनकर आज आपका नाम नींद में भी उठाता है तो आपका नाम बोल पा रहा है, क्योंकि बहुत बार सुन लिया. That means you contemplated or you come across it many times. If you want any knowledge to not to भूल जाना चाहिए, उसको क्या करना है, आपको बार बार याद करना चाहिए. बार बार याद करता है तो याद आ जाएगा. ठीक है. So nobody in this world is a याद नहीं आता है करके नहीं बोलना है, because he is lazy guy only can not do any work. If you are not lazy, you can do a simple contemplation. You know, need to take the 1000 kilo means
But sir,
100 kg.
why to remember when we have all those devices to store that data?
Yes. So nowadays this neural energy neural concept is coming into the science also. That is called big data science, or otherwise artificial intelligence. Machine learning is now they understood the brain knowledge, brain science. So that's why it is coming into existence in even in the every field.
So there isn't any need to remember things. We can just have a look.
No, some things you have to remember. For example, if you want to invoke, for example, today I want to press my password. You have to remember, right?
Yeah, passwords. Okay.
Means, for example, you want to enter, you want to create a program. You want to enter into a mission. Some memory should be there. At least your memory means your neuron memory is so nice that today you are able to stand because it was confidence is given at the time of your childhood to your neurons.
But I don't remember, sir, any formula or other things. It is usually hard to remember. So I
No, not these formulas. For example, आपको कान लाइट चली जाने के बाद आंख बंद होने के बाद भी आपका हाथ मुंह में भी जा रहा है खाने के समय. क्यों जा रहा है, कैसा जा रहा है? That is also memory. Yes. So some memories are the very important memories. For example, if I am asking your name, you are tak bata raha hai Hamid. वो किधर से आ रहा है?
Yeah, Hamid, you are going to use a neural network to tell your name.
Yeah. So what I want to say is that some of the even I got an accident. I broke my leg. So initially, first 1 month when I am walking, I forgot because my neurons are damaged. So इसको फिर से बताना पड़ेगा. ऐसी तरह होता है तो आप कड़ी कर सकता है, उसको लूज नहीं होगा ये डायरेक्शन में, इस तरफ से ही इसको पास करना है. बिकॉज सम डैमेज हो गया तो और सम डिस्टर्बेंस हो गया तो उसको फिर से बताना पड़ेगा. मे बी यू माइट हैव नो सम पीपल लॉस्ट देयर मेमोरी एंड ही डोंट नो इवन हिज नेम बिकॉज देयर इज अ बिग डिस्टर्बेंस, बिकॉज ट्रूमा हो गया, कुछ तो हो गया उसका लाइफ में, इसकी वजह से पूरा डिस्टर्बेंस हो गया मेमोरी में. So then they may forget how to stand also, how to walk also. This is what in the old age mein people may, because many of the brain cells damaged, they lost memory, they lost slowly even walking capacity, even remembering. For example, uska ghar ko wo bhul jata hai because some of the damage is happening inside because of the old age. That's why our human life is completely limited. Only for 60 to 80 years because इसका भी bell shape है. After some extent your memory is not able to support you many things, right? Those are all the memories, different kinds of memory. That's why I told 100 तरीका का है. इसका अंदर कुछ तरीका ही हमको अभी मालूम है हमारा brain का. Remaining things like walking things, फॉर एग्जांपल इनसाइड बॉडी को एडजस्ट करना भी हो जाता है, वो सब बॉडी का अंदर से होता है, आपको बिना पता चलकर अनकॉन्शियसली देयर आर टू ब्रेन्स करके, एक इज ए कॉन्शियस ब्रेन, अनकॉन्शियस ब्रेन. सो वो अनकॉन्शियस ब्रेन विल वर्क व्हेन यू आर स्लीपिंग. सो दीज आर ऑल डिफरेंट मेमोरीज दैट वर्क्स. Anyhow, this is a metaphysics, we don't want to enter much.
Yes, sir.
But we should aware that it is working in our life for the smooth functioning.
Yeah.
वो अवेयर होना ही है, उसको भगवान बोलता है, वही अवेयरनेस को भगवान बोलता है. सो वही हमको चलाने दे रहा है, हमारा अंदर से वो एनर्जी देकर कौन चला रहा है हमको. एंड ये चलाना वाला ये बॉडी से चली गया तो इसको शिव के शव बोलता है. सो दैट इज द थिंग्स. एनीहाउ वी विल गो हेड, गो फॉर अ फूड नाउ. सो दिस इज एनफ फॉर टुडे. I think Kishore sir is unnecessarily locked because he is a moderator. Thanks for Kishore sir and all the students who are patiently listening and fasting with me up to this time. So you can break your fast.
Okay, sir. Thank you.
Thank you very much.
Have a nice day.
Yeah, thank you. हम जा सकता है